Ladies and gentlemen, it is my distinct pleasure to be the host of this session on security and cryptography. The first speaker of the session is Professor Amit Sahai, my colleague at UCLA. Amit is a semantic chair professor of computer science and the founder and director of UCLA's Center for Encrypted Functionalities. It's an NSF Frontier Center. Amit is the co-inventor of attribute-efficient encryption, functional encryption, indistinguishability obfuscation, among other pioneering notions in cryptography. For his breakthrough contribution, cryptography and security, he is the recipient of numerous honors. Among others, Amit is a fellow of the ACM, a fellow of the AICR, a recipient of a Sloan Foundation Research Fellowship, an Akawa Research Grant Award, a Xerox Foundation Faculty Award, a Google Faculty Research Award, a Paisley Memorial Award, an ACM CCS Test of Time Award, and an IACR Test of Time Award, among many other honors. Amit will be joined in this presentation by his two co-authors. The second part of the presentation will be delivered by Rachel Lin. Rachel is a professor at the Paul Allen School of Computer Science and Engineering at the University of Washington. Her research interests are in cryptography and the interaction in the interplay of cryptography with other areas of computer science, such as complexity, algorithm design, and security. Prior to joining UW, Rick spent 5 years as an assistant professor at the computer science department of the University of California, Santa Barbara. She is a graduate of Cornell University, where she completed her PhD under Rafael Paz. Following that, she was a postdoctoral researcher working with Shafi Goldwasser and Ron Canetti. The third speaker of the session, delivering the third part of the tutorial, is Aayush Jain, a PhD candidate in our Department of Computer Science at UCLA and a PhD student of Amit Sahai. Aayush is a star student in our department, and he has won just about every single honor that a student in theoretical computer science can aspire to have at this stage in his career. He has been awarded the Semantic Outstanding Graduate Student Award at UCLA, insanely competitive. He has been awarded the Google PhD Fellowship Award in Security and Privacy. He is also a recipient of a DAX Award for a special focus in cryptography. The work that you're about to see in this tutorial has been covered by a variety of news outlets and blogs and Twitter, and it's an exciting breakthrough development in cryptography and security. So I'm absolutely thrilled to introduce our three speakers. I turn the floor over to them, and they will run the presentation while monitoring the let's see, the chat and the Slack channel. So if the live audience has questions, I'm sure the presenters will be absolutely thrilled to take them in real time to make this more interactive. Okay, please join me in welcoming Amit, Rachel, and Aayush. Thank you.
All right. Thank you, Sasha, so much for that really generous introduction. And absolutely, please do interrupt us. We would love to take questions. The whole point of this interactive Zoom-based tutorial is for us to be able to have this be more interactive. And it's an intimate setting. Sasha, I do want to just confirm, are we recording? Is the recording on? I didn't get the little thing that I usually do when
yeah. So there's a little there's a little red circle that's blinking. It says recording. In general, all FOCS sessions, all tutorial sessions are recorded automatically, so awesome. We don't need to record it.
Okay, excellent.
Kamesh told me in advance that they're going to be recorded automatically. Yeah.
All right, that is great to hear. And so, indeed, I'll be talking about indistinguishability obfuscation for well-founded assumptions. This is part one of a three-part tutorial. And this work is really the result of a wonderful multi-year collaboration with Aayush, Jain, and Rachel Lynn, who have already been introduced. So let me jump straight into it. Let me try to jump straight into it. Okay, so what kind of problem are we talking about here? Suppose that you want to keep a secret, okay? But unfortunately for you, there's an adversary, excuse me, that has captured your entire brain. So it's ripped your brain out of your head, has complete control over it. It can read your brain, it can tamper with your brain, and it can understand everything that's happening in your brain while you are thinking about some secret that you want to keep, okay? So of course, I hope this never happens to you. I haven't heard of it happening to any human being yet, but it's kind of a terrifying idea that, you know, even your sort of the sanctuary of your own mind is being violated by an adversary that wants to extract a secret from you. And, you know, thankfully, again, this doesn't seem to happen to us humans. But if you think about it, this happens to the poor computer science analogs of brains all the time, right? So the analog of a brain in computer science is a computer program. And computer programs get captured by adversaries all the time. In fact, we usually just give them away to the adversary, right? So if we're selling a program, that means an adversary can buy it, download it, and examine it, examine every single line of code, tamper with it, do whatever it likes, trying to extract some secret out of that code. And again, the question that we're asking is, can we actually get a computer program to keep a secret even when the adversary has captured the entire program? It's a mind-reading adversary and a mind-tampering adversary with respect to this computer program, right? And just to stress, we're talking about a situation where there's no trusted hardware. The hardware is completely public. Everyone knows how every aspect of it works. There's no interaction. There's no communication with some server or anything like that. It's just an ordinary program. It has ordinary inputs, ordinary outputs, no encrypted inputs or encrypted outputs, just normal inputs and outputs. And again, it's running on a single, completely ordinary computer, right? And again, that is the sort of almost fantastic sounding problem, you know, that we're trying to attack, okay? And if we take a step back and think about in cryptography, the sort of question of keeping secrets while there's a computation going on, there's actually a rich history of trying to keep secrets, you know, within a computation. Most notably, the classic work of secure multi-party computation due to Yao, Goldreich, Macaulay, and Wigderson, Benro, Goldwasser, and Wigderson, and really hundreds of follow-up works. And to take the sort of analogy of the brain, what these earlier concepts would correspond to would be sort of taking this brain of ours and subdividing it into lots of little parts, okay? And now the adversary can see into and tamper with, let's say, one of these parts, or in the most advanced form of secure multi-party computation, the adversary could see into and tamper with all but one of these parts of the brain, okay? But on the other hand, in all this classic work on secure multi-party computation, it was always assumed that there was one part of this brain that was completely blocked to the adversary. The adversary had just no idea, excuse me, what was going on in some one part of the brain, and that part is just, you know, behaving honestly. And so, as you might imagine, the basic concept that was used to achieve secure multi-party computation was the idea of kind of spreading out the secret and the computation, and this idea of secret sharing, where where a secret is divided into lots of little parts, and actually you need all the parts of that secret to be able to recover the original secret. And since the adversary is blocked from one part of the brain, here the adversary won't have access to all the parts of the secret, and so secrecy will be maintained. It's a beautiful idea. Lots and lots of work has been done on developing that idea and you know, playing with it in various different contexts. But again, it's fundamentally different from program obfuscation, from the problem that we're looking at. because again, in general purpose obfuscation, no part of the computation is hidden from the adversary, right? Unlike here, where there's a portion of the brain that's blocked off, in program obfuscation, the entire brain is given to the adversary. And so that really fundamentally changes the nature of the problem, and it is what makes the problem so challenging and fascinating. So what do we mean more formally by general purpose program obfuscation? So I'm going to give you a definition called indistinguishability obfuscation. This was proposed in a joint work with Boaz Barak and many co-authors back in 2001. And what we defined was that IO is a probabilistic polynomial time algorithm, and it's a compiler. So it takes as input some computer program. And for the purpose of this talk and this tutorial, we can think of the program as being represented by a Boolean circuit. So it's some circuit with some number of inputs and some number of outputs. This compiler, IO, it takes as input this Boolean circuit and outputs an equivalent Boolean circuit. So the input-output behavior of the program is identical post-obfuscation. And furthermore, the running time or the size of this circuit is at most polynomial in the original running time. So the obfuscation mechanism, the IO compiler, can't slow down the program too much. You can only slow it down by a polynomial factor. Okay? And then finally, what is the security definition? The security definition states that if we start with two equivalent programs, P0 and P1, of the same size, so again, think about it as two circuits that compute the same function and have the same number of gates, then no polynomial time adversary should be able to distinguish between the obfuscation of P0 and the obfuscation of P1, even when given these two programs, P0 and P1. In fact, the adversary can even choose the two programs, P0 and P1. And nevertheless, once it's obfuscated, he shouldn't be able to do much better than random guessing in terms of guessing whether the obfuscation came from P0 or came from P1. Okay. So let's take a moment to think about this security definition. And once again, please do interrupt and ask questions whenever you would like. So what is this idea of indistinguishability obfuscation? How can we kind of intuitively think about it? We can think about it as being a kind of pseudo-canonicalizer. That is, that suppose it was possible, right, to take a program and convert it to some canonical form that only depended on the input-output behavior of that program, then would clearly satisfy this indistinguishability property because IO of P0 would be equal to IO of P1. It would just equal the canonical form. So that's not what we get. We don't actually get a canonical form, but we get sort of a pseudo-canonical form, right? We get something that is indistinguishable from the canonical form of the program. And therefore, we know for sure that IO of P reveals nothing more than a canonical form of the program would reveal, right? And in particular, if there are many different ways you can compute a certain function, then the canonical form won't reveal which of those ways you chose. And similarly, IO of P will not reveal which of those ways you chose to implement it. And this leads to sort of a curious fact, a curious little observation, which is that if P equals NP, then in fact IO exists, for sure. And why is that true? It's just because if P equals NP, then the hierarchy collapses, and it's actually possible to compute in polynomial time the lexicographically first circuit, right, that computes the function that's given by some input circuit. So because that can be computed in polynomial time, an actual canonical form, it would, of course, achieve the definition of IO. And again, this is just very interesting and sort of curious fact because, typically in cryptography, P equals NP is just devastating. All of cryptography that is at least public key cryptography, like public key encryption, it all just falls away if P equals NP. Whereas interestingly enough, IO doesn't. IO would actually exist if P equals NP. Of course it would exist, but we wouldn't know much about what we would do with it. It wouldn't be terribly useful for cryptography, but it would exist. So just kind of a cute observation. All right, so great. So we have a definition, we have formalization, all these things can be made very precise. It's extremely fascinating notion. Hopefully I've convinced you of that. But indeed, as Rachel also mentioned in the pre-tutorial time period, not only is it super fascinating, but it turns out to be incredibly useful as well from a theoretical point of view. And indeed, if we think about sort of the crypto world up until the advent of IO, of course, it's a beautiful, beautiful area that I've loved to work in, and lots of amazing concepts that were around. But once we got IO, and then especially using a technique called punctured programming that we devised in a joint work with Brent Waters back in 2014, it turned out that IO actually is incredibly useful. And there's sort of a whole new world of cryptographic applications that opens up. These are just a few of them. And in fact, there are many, many more, really more, certainly much more than I have time to talk about. In fact, we could have an entirely separate tutorial on just applications of IO, and even with 3 hours, we wouldn't be able to even just see the surface of what is possible. And again, one of the things that makes it so exciting is that it's not just that that we get a bunch of cool cryptographic applications, but in fact, IO even expands the scope of cryptography. There are problems that we wouldn't have thought of as being amenable to attack through sort of mathematical cryptography that now become in scope for cryptography because IO deals with the computer program itself, right? Hiding its secret within a computer program. So that's another sort of fascinating aspect of it. Again, I wish I could go into more detail, but I just don't have time. And in fact, it turns out that IO is also useful for going back to sort of our old world of crypto and getting interesting, better in various concrete ways, public encryption, short signatures, non-interactive zero knowledge, and many other sort of classic notions from cryptography. So, so there's, again, a wonderful, rich body of work here to think about that we will not cover in this tutorial. The purpose of this tutorial instead, of course, is to think about how to construct IO. How do we actually build this, this beautiful and fascinating object? So let me sort of take a historical viewpoint. And I do want to just say in advance that I'm going to kind of stroll through the history of constructing IO, and I won't be able to talk about most of the papers on constructing IO, so I apologize in advance for missing references. Some of those references will be found in future sections of this tutorial. But basically, for the first decade since our work where we introduced the definition of IO, basically nothing was happening. So if you look at the published work, you will see 0 papers on constructing IO. And of course, what that means is that for about a decade, there's a sort of a graveyard in the sky, right, of all of these ideas that people had that didn't work for constructing IO. And I can personally attest to at least some of those tombstones of ideas that I thought about that didn't work. And I'm sure there are many, many more that other people thought about and just weren't able to get to work, right? And in fact, the situation was even more bleak because this work that I was mentioning, the work with Boaz and others, really the focus of that work was not to define IO. The focus of it was actually to prove impossibility of other related notions of obfuscation. And in fact, there were other works that followed up as well that proved such impossibility results. So in general, the first decade after the introduction of the definition of IO was quite bleak in the sense of just seemingly no ideas, no approaches for how to construct IO. This changed in 2013 in a joint work with Garg et al., where we showed how to use a new and fascinating cryptographic object called a cryptographic multilinear map to construct IO. And cryptographic multilinear maps are really interesting objects that we will not be going into in any detail in this tutorial because we don't need them, we're not going to use them. But I'm going to talk a little bit about them sort of historically. Roughly speaking, they're ways of computing certain polynomials in a private way, and in a way that wasn't known before, but in 2013, some new ideas came along to try to do that. And then we showed how to use these new objects to build IO. And the assumption that we needed was quite complex, completely new. But we thought, maybe okay. In general, in crypto, we've been reasonably lucky in coming up with new assumptions and having them hold up. So we thought, why not? Let's try it. Let's go out on a limb and try something. But unfortunately, in the years to come, a number of weaknesses are found in cryptographic multilinear maps. And then finally, in a joint work with Miles and Zandri, we were actually able to break not only the underlying maps, but even the IO candidates that resulted. And this was followed up in a work by Apone et al. That was sort of even more devastating in terms of their impact on IO candidates. So again, it seemed like kind of bad news for this construction. There was also a work by Craig, Allison, and Brent, and then followed up with another work also with me, where we gave a simpler assumption, again using cryptographic multilinear maps. Again, unfortunately new, maybe okay, and once again, our hopes were dashed. The pioneering work of Jain et al. And Corona, and some joint work with Corona et al. Broke again those assumptions that we were making, the simpler assumptions, and once again, we didn't seem to be getting anywhere from that. In another few years after that, in some joint work with Badri Narayan et al. And Garg et al., we showed how to relax this notion of cryptographic multilinear maps to something we call weak cryptographic multilinear maps, and showed that those are actually sufficient also to build IO. And this is a new algebraic model in terms of assumptions. It did seem to avoid the attacks that we had so far. And it was quite interesting in that way. In fact, still 4 years later, we still don't know any attacks on these schemes and, with appropriate choice of parameters. But frankly, it was also the case that the work that we did, the constructions we came up with in this way, we weren't seeing too many moving parts. Like we wouldn't see how to bring this down. How could we take these weak multilinear maps and bring them all the way down to sort of well-founded assumptions that was just not obvious to us with that particular line of work. There was another line of work that was started with the really pioneering work of Anant and Jain and Bitansky and Vikuntanathan, and a breakthrough work of Lin in 2016, and then a number of follow-up works that took us, in terms of building IO, all the way down to just degree 3 multilinear maps. These are like, things that can somehow evaluate degree 3 polynomials in a private way, together with some well-established assumptions like the learning with errors assumption and PRGs with constant depth circuits. And this was sufficient for building IO, which again was really, really exciting. But unfortunately, once again, it turned out that the degree 3 version of multilinear maps were actually no more secure than the general degree version of cryptographic multilinear maps. And actually a number of attacks also broke all of these assumptions that were being made over degree 3 cryptographic multilinear maps. But again, there was some kind of progress. These assumptions were simple to state, even if without any instantiation. Okay. Then there was some new work that came out that was able to get IO from, again, some well-founded assumptions, including some assumptions that were bilinear maps that were well established, and a new object that was a degree 2 pseudorandom object. Again, there was a little bit of optimism at this point, but again, our hopes were dashed, and this time actually in a quite theoretically fascinating way. So using the sum of squares paradigm and sort of classic semi-definite programming based optimization techniques, for the first time, those kinds of semi-definite programming ideas were actually used to break cryptographic objects. As far as I know, this is the first time that the sort of classic optimization techniques were used successfully to cryptanalyze interesting cryptographic objects. And this is done in a work by Barak et al., by Lombardi and Vikuntanathan, and a joint work with Barak et al. Again, all using the sum of squares. But once again, the bottom line was that one more idea was proposed and it was broken. So at this point, it's fair to say that there was some turmoil in the community and a bit of a rush for the exits. There was a note that was called In Pursuit of Clarity and Obfuscation by Allison and several co-authors. These are all people who had spent, hundreds of hours working on constructing IO. And this note was kind of a lament about the current situation when it came to constructing IO, which, was not very hard to understand. The situation did seem quite turbulent with all of these ideas and attacks and refinements and attacks and this sort of cycle continuing, which was troubling. And it was just around this time, actually in 2017, that I was preparing a talk on constructing IO, and I ran across this really beautiful article in Nature by the physicist Steven Weinberg, and he wrote the following. So let me quote from him. He said, quote, "A student told me that he wanted to go into general relativity rather than the area that I was working on, elementary particle physics, because the principles of the former were well known, while the latter seemed like a mess to him." Weinberg continues, "It struck me that he had just given a perfectly good reason for doing the opposite. My advice is to go for the messes. That's where the action is." And I think this quote is sort of very appropriate, and I found it very appropriate at that time, and I still do, because really, IO has really been sort of a wonderful mess since 2001 when we first approached it. Really, an area that has seemed like wilderness with a great deal of difficulty in terms of attacking it. And I think that if we're honest with ourselves in the stock FOCS community, it is quite different from the typical theory work that we do in stock FOCS, where we typically try to optimize some algorithm or come up with a better approximation ratio or hardness of approximation result from assuming P not equal to NP. There's sort of well-defined lines that we typically try to attack. Now, of course, all of those also have messes underneath that we're taming. So, of course, taming messes is essential to any sort of research. But this type of taming work, where it really is unclear, when is it that we have a result? It's what assumptions, if we're going to make new assumptions, when are they reasonable? When are they not? This is something that has been quite difficult. And, definitely I have had quite talented PhD students who, when I introduced them to work on IO, they did come back and say, "Amit, please, no, I don't want to work on this. And can you please just give me some concrete conjecture, that I can try to prove? I don't really know. When are these assumptions reasonable?" And that's a reasonable, perspective. And it is difficult, I think, for us with our sort of usual training and perspective in the stock FOCS community to sort of attempt these sorts of areas. But they are mathematical areas. And of course, it is absolutely our duty as theoreticians to tame these messes. And so I really do think that it is our job to do it, and we definitely should try to do it. And in terms of this question about, well, when do we know we're making progress when things are so messy? So these little angels that were popping up in my slides, they weren't just bad ideas that were going to crypto heaven. The reason why I put them there was actually all of these papers that had little angels pop up next to them. Yes, the assumptions that we're making didn't work out, but actually each of those papers had a key idea, at least one, or many times more than one key idea that was underlying them. That was an essential lesson for us that helped us take this path. And obviously, I'm here talking to you, and all of us are here in this tutorial talking to you because it did work out, right? We were able to eventually tame this mess. That's what we're telling you about now. But it didn't just come out of nowhere. It was this messy process, lots of these little angels that came up and told us things about how we should attack this problem, you know, what kinds of limitations there are, what kinds of weaknesses we have to avoid when we're constructing IO, and also what recipes, even if they didn't have a way, even if we didn't have a way to instantiate them, what are the recipes that actually have more moving parts, have more, you know, room for development, where we can keep developing and keep trying to push the envelope. So now let me come back to the sort of storyline, and indeed, this this line that, you know, had that started with these degree 2 objects led very naturally in sequence of our works to assuming some sort of new, what we'll call leaky pseudorandom objects, and showing how to use these new leaky pseudorandom objects to build IO, again, when combined with with standard or well-founded cryptographic assumptions, lower bilinear maps and PRGs and constant depth circuits and LWE. Nevertheless, this assumption itself, the assumption that this particular types of new leaky pseudorandom object exists, was an unusual and new assumption, but again, quite simple, especially in contrast to the work that had come before us. And again, we chose this leaky pseudorandom object in a way that would avoid the sum of squares attacks and other attacks that we were aware of. There was insight that, you know, came into the way we formulated it that turned out to be crucial. And indeed, of course, the reason why we're talking to you today is that a few months ago in our joint work, we actually showed how to build IO assuming only well-founded assumptions. So in addition to the 3 that I've already mentioned, we also assume the LPN assumption over finite fields of prime order. And indeed, we use these assumptions to first build a new pseudorandom object, a kind of leaky pseudorandom object. But now we do it in a provable way. We don't have to assume that it exists. We can actually just prove that it exists using these assumptions, especially this LPN over ZP assumption. And that takes us all the way to IO. So with that, I'd like to now transition to the technical part of this tutorial. And I'll start with this first assumption, which is in some sense the most interesting of the assumptions that we make, which is the LPN assumption over prime fields. So this is also a good place to just pause and see if there are any questions about the history. All right, if there are no questions, let me go right ahead and get into the technical meat. So what is this LPN assumption? This LPN assumption actually, again, has a long history in cryptography, dates back to the pioneering work of Blum et al. From 1993 in terms of its use in cryptography. But really, the assumption itself dates much, much further back to the 1950s, at least the 1950s. And it has to do with the theory of error correcting codes over finite fields, in particular the theory of random linear codes. So what's a random linear code? A random linear code, in our context, is described by a public matrix A that has n rows, so it's kind of long. It has n rows and L columns, so it is longer than it is wide. And to encode a short message S, we simply left multiply S with our matrix A to obtain our n-dimensional code word C over ZP. Okay. And now, why do we care about these kinds of linear codes, especially these random linear codes? It's because, again, back in the 1950s, in the classic and extremely influential works of Gilbert and Varshamov, it was shown that random linear codes actually exhibit incredibly strong combinatorial error correcting capabilities against sparse error. So for the purpose of this talk, let me make that as precise as I can. So we consider an n-dimensional vector E, which is very sparse. It's almost always 0, except with probability 1 over L to the delta, where delta is some constant greater than 0, any constant delta greater than 0. With probability 1 over L to the delta, it is just a uniformly random number in the finite field ZP. Okay, and again, remember L is a dimension of S, and delta is again smaller than 1. It's closer to 0. So what that means is something like 1 over every, let's say, 10th root of L entries in E will be non-zero, again, chosen at random. Okay? And again, it was known since the 1950s that, combinatorially speaking, given A and AS plus E, there will always, with overwhelming probability, be a unique vector S that such that AS plus E is close in Hamming distance to AS, to the code word S that encodes S. And so we know that, again, information theoretically, it is possible to recover S from AS plus E. However, remarkably, again, since the 1950s, despite decades and decades of work, there has been essentially no progress whatsoever in efficiently decoding such random linear codes with sparse error. And here by efficient, we actually even mean just, we actually mean sub-exponential in L. So there are no known algorithms that are like 2 to the L to the epsilon in complexity that given A and AS plus C can recover S. And that naturally leads to our assumption, where what we assume is that AS plus C is actually computationally indistinguishable from a completely uniform vector U. And what we mean more precisely is that there exist arbitrarily small constants, epsilon and delta greater than 0, where again delta was a parameter for the sparseness of E, such that this assumption holds for all time 2 to the L to the epsilon adversaries. So good. And it turns out that assuming this kind of indistinguishability actually does follow from the hardness of decoding that I was just talking about. In other words, if we assume that it is sub-exponentially hard, again, 2 to the L to the epsilon hard, for an adversary to recover S given A and AS plus E, then it follows that it's 2 to the L to the epsilon prime hard to distinguish A comma AS plus E from A comma uniform. This is because of a classic search to decision reduction that can, for example, be found in the 2011 work of Michianchu and Moll. And in fact, when it comes to attacks, in terms of how well do we know how to do this, the best known attack, despite, again, decades of effort, actually runs in time 2 to the L to the 1 minus delta, again, where delta is an arbitrarily small constant. And all we are assuming is 2 to the L to the epsilon security for an arbitrarily small constant epsilon. And here is just a slide that I borrowed from Geoffroy that talks about just a sort of a sampling of the really dozens of papers that have tried to attack this problem over the last few decades. And again, despite all of this work, the best known attack is 2 to the order L to the 1 minus delta. And we're only assuming a much weaker assumption, which is 2 to the L to the epsilon. And again, we're only assuming it for a relatively high degree of density, meaning when delta is just any constant greater than 0, rather than significantly more sparse assumptions where the assumption is somewhat, the assumption is stronger. And indeed, I mentioned that because that's in contrast to most applications of LPN in cryptography, where we typically need to assume this is true in the case where delta is greater than 1/2, for example, to build public key encryption. That's a stronger assumption as far as we know. Again, we only need this to hold when delta is an arbitrary constant greater than 0, which is not enough to build public key encryption. It's too weak an assumption, but that is the only assumption that we actually need from LPN in order to reach IO, given the other assumptions that we make. And just to make this more concrete, instead of with pictures, this assumption states that if we have these vectors AI, we have n of these vectors AI and the vector S, all L-dimensional vectors, then given these vectors AI and the inner product of AI and S plus EI. This is computationally distinguishable from AI comma UI, where UI is just a uniformly random element from ZP. Right, so this is a restatement of what I wrote in pictures earlier, in matrix form earlier. And again, we want this to hold against 2 to the L to the epsilon time adversaries. Okay. Any questions about this, about the assumption? Please do interrupt if you have any questions about it.
So for this assumption, is there like some kind of a dependence known for P, like for large P, is it easier or?
Good question. Excellent. Yes. So it turns out that historically, the assumption was first looked at in the crypto context with P equals 2. And most of the use of it was with P equals 2. But it turns out that from an algorithmic point of view, in fact, if anything, the P equals 2 case seems only easier than the general P case, in the sense that there are some algorithms that are known that still only achieve roughly, 2 to the L to the 1 minus delta, is slightly better than that complexity for P equals 2. But where those algorithms would not work for higher values of P, for general values of P. So we do need to make it for P of sub-exponential size. I kind of hid that under the rug. Roughly the size of P will be 2 to the L to the epsilon prime, where epsilon prime is even smaller than epsilon here. But again, from a hardness point of view, we have no evidence that it is any easier. In fact, we only have evidence that it is potentially harder when this assumption is made over ZP for larger values of P. At the same time, in cryptography, typically we've looked at it with P equals 2. The assumption for higher values of P was only made for the first time, as far as we know, in a joint work with Yuval Sahai and Manoj Prabhakaran back in 2009. But then it has been used by several works since then in the context of constructing public encryption, but also in the context of secure computation for algebraic computations. So not in the context of IO at all, but in other contexts. Does that answer your question?
Yeah, and I had a more basic question, in the sense that what exactly do you mean by well-founded assumption? Is it like, like the failure of that to hold, does it imply something else that we kind of believe in a more stronger sense, or is it like a non-technical?
Right. Good question. We are using it here in the following way. We will call an assumption well-founded if it has, again, a long history of study and that it's been made in completely other contexts in cryptography, right? That it's not an assumption that we just are making for the purpose of IO. And again, also this has a history which is, with lots of attacks and again, it's been looked at since the 1950s. So in that way, we call it a well-founded assumption. But in terms of some other concrete technical meaning, we do not mean anything else. We just mean that it has a long history of study, and it's been used in cryptography for building other cryptographic objects that have nothing to do with IO or any related concept.
Okay, thanks.
Sure. Any other questions about this? All right. Please do interrupt if you have other questions. Okay, great. So this is our assumption. And again, it's been around for a very long time. And I want to give you just a little bit of a hint now as to how we're going to make use of these kinds of assumptions, and in particular, this LPN assumption in our work. And we'll just give you just sort of a brief taste of the types of cryptographic arguments that we're going to be making in this tutorial. So let me go ahead and do that. And I'm going to talk about this in the context of this new pseudorandom object, right? So I mentioned that prior to our work, in our earlier works, we just needed to come up with a pseudorandom object and just assume that it was pseudorandom. We needed to just make an assumption that it was pseudorandom without knowing how to prove it. And what's new about our work is we're going to build a pseudorandom object and actually prove that it's pseudorandom And indeed, the LPN over ZP assumption will play a starring role in that proof. And I want to give you a sense about that right now, okay? And in fact, the proof will be extremely, extremely simple. So please, every single person who is listening to this right now, all of you should understand this completely. If not, then please, please ask a question about it, okay? This is the briefest, gentlest introduction to the kinds of arguments that we're going to be making, okay? So, and this pseudorandom logic, as I mentioned before, is at the heart of our work, and it is very closely related to the previous objects that we were studying in our previous line of work. Right now in this, part one of this tutorial, I'm only going to talk about the output of the pseudorandom object and not how it's computed, although that's a very important aspect of our work, but you'll hear more about that in part 3 of the tutorial, okay? To kind of give you an ad, I'm going to talk to you about the output and proving that the output of the object is pseudorandom. So the output of our object has 2 parts that are unfortunately and kind of annoyingly correlated. Okay, and this is something, this correlation was there in our previous works as well. Okay? So the first part looks a lot like the distribution from LPN over ZP. Here we have our vectors AI and our secret vectors S and our error vectors EI that are from exactly the same distribution that I already mentioned. AI and S are totally uniform, EI is sparse and uniform when it's not sparse, okay? But in addition, we also have a bunch of Boolean values, x1 up to xn, which are chosen at random, okay? And the first part of the output of our object has AIs and then AI.s plus EI plus XI, okay? So far so good. Now the kind of tricky part is that there's a second correlated output where we take these xi's, these Boolean values, x1 up to xn, and use them as a seed for a standard pseudorandom generator, okay? Now, all of you looking at this should, tut-tut at us and say, oh, no, this is not good, because everyone knows that when you're using a pseudorandom generator, you should just use the seed to compute the pseudorandom generator, and then you should just throw away the seed. You should never use it again, right? Like, it's good hygiene to use a seed once and then never use it again when we're dealing with pseudorandom generators. And here we're not doing that, right? We are using the seed both as the seed to the pseudorandom generator, but also as a sort of additional noise in this first part here, where we have AI.s, but then in addition to that, plus this sort of sparse noise, plus this Boolean noise xi, right? So this is something sort of non-kosher that we're doing. What we're going to show us is that, what we're going to show you is that, in particular, now that we're doing it using LPN in this particular way, in fact, it does not present any barrier to pseudorandomness. And we will actually prove that to you right now, okay? And again, the proof is extremely simple, okay? It's almost trivial, okay? So we started again with this output, right? We have the left output, which is AI and AI.s plus EI plus XI, and the right part of the output, which is the output of the PRG on input on the seed x1 up to xn, okay? And we need to prove that this is pseudorandom. So the first idea is, let's just apply the LPN assumption, right? Because after all, we have what looks like an LPN sample just sitting right here. And the LPN assumption says that this part of the sample looks uniform, right? And again, more formally, what do I mean here? What I mean is that I can convert an adversary that can distinguish between this output and this output into an adversary that breaks the LPN over ZP assumption. How? My reduction adversary will simply choose x1 up to xn itself, just at random. It will take externally an LPN sample that will either look like AI and AI.s plus EI, or it will look like AI, UI. And then I'll just add xi myself to it. I'll compute PRG of xi myself because I chose it myself. And now I'm either going to have a sample from the top distribution or a sample from the bottom distribution. And then I can give this to my adversary. If the adversary can distinguish, then it is distinguishing between the LPN AS plus E version, or the uniform version of the LPN sample, right? So in this way, we immediately have a proof that the output of our pseudorandom object, in fact, is indistinguishable from AI comma UI plus XI, and then the PRG of X1 up to Xn, okay? And again, please ask questions if there's anything missing here. And then the second observation is, again, just completely trivial, which is that if I have a uniform value UI and I add a random bit to it, it just is a uniform value. Like adding a random bit to a uniform value does not make it any less uniform. And so this distribution is just identical to the distribution, which is just AI comma UI, and then PRG applied to X1 up to Xn, right? And now that we've done this, note that we're no longer using the seed in any non-kosher way, right? The seed is only being used as the input to the PRG. So now we can just directly apply the pseudorandomness to the PRG and conclude that the output of our pseudorandom object is in fact pseudorandom. It is in fact indistinguishable from just completely uniform AIs, UIs, and capital R as shown here, right? So in this extremely simple way, we use the LPN assumption to show that this particular output is in fact pseudorandom. And in fact, let me tell you, this is the only place that we will use the security guarantee of the LPN over ZP assumption. This is the only way we're ever going to use it, just in this extraordinarily simple way, okay? And what are we doing, right? In this extremely simple way, we've used the LPN assumption to kind of break up this dependency, right? By adding this sort of intermediate error EI to this other Boolean error XI, we were able to break apart this annoying dependency that existed between the left and the right side of the PRG, and thereby conclude pseudorandomness. And really, this is the new thing in our work. In our previous work, we also had some sort of correlations between the seed and the error, but we couldn't break it apart like this. And that's something that is important to this work. Okay, so again, this is just a little brief preview. There's much more to this that you will hear more about, especially about the pseudorandomness here in part 3 of the tutorial. Okay, if there are no questions here, then let me move on and talk a little bit about the other assumptions that we're making. So the next assumption that we'll make is what's called the learning with errors assumption. And this is just like the LPN assumption that I just told you, except the only difference is in this error distribution. So in the LPN assumption, the error distribution EI is sparse and uniform when non-sparse, whereas in the LWE assumption, the error is small and Gaussian in every component. So it's not sparse. Instead, every single component has a small noise that is Gaussian. Okay, and the version of the LWE assumption that we make is with sub-exponential modulus to noise ratio. That means that the magnitude of each entry of EI is sub-exponentially smaller than the prime P that we're working over. Okay, and again, this is a well-trod assumption. In particular, it's known to be true if the shortest vector problem over general lattice is worst case hard to approximate to within any sub-exponential factor. This is due to this beautiful and Gödel Prize winning work of Regev and Pikert and Bukursky et al. That showed this, this worst case to average case reduction. And also I should mention the same search to decision reduction also applies to LWE, the same one I mentioned by, that's for example, shown with Jianchu and Mo, which again shows that if I can recover S from AS plus E with this type of small Gaussian noise, then if that's sub-exponentially hard to do, then the distinguishing version is also sub-exponentially hard. And really this LWE assumption is extremely useful in cryptography, and it's being used for really a remarkably versatile number of applications in cryptography, most famously for constructing fully homomorphic encryption in the breakthrough work of Brzezinski and Vikranthanathan. So LW, again, is a very well-trod assumption in cryptography, beautiful and well explored, and we're also going to be assuming it. But now, let me just see to make sure that all of you have been paying attention. If you think about it, this LWE assumption is really very much like the LPN assumption, right? The only thing we changed was the error distribution. And so if we go back to this argument that I was just making, observe that this pseudorandomness argument could have worked just as well if we had used LWE errors instead of LPN errors, right? If these EIs had been small, then using the LWE assumption, we could have made this first step of our analysis work, right? So in fact, in the pseudorandomness analysis that I've already mentioned to you, there's really nothing special about LPN that we're using, about the sparsity that we're using just to prove pseudorandomness. Nevertheless, the fact that LPN errors are sparse is absolutely crucial for us. It's absolutely critical and really the heart of our work. And the sparsity of LPN errors is going to be used for suitably computing the pseudorandom object. Not its output, but its actual computation. How can we compute it as efficiently as we need to compute it? That's something that you will hear more about in parts 2 and 3 of the tutorial, and the details of this will come in part 3. So, so with that, let me briefly mention the other assumptions. We also assume, as I mentioned, that we have pseudorandom generators that are computable by constant depth, in other words, NC0 circuits, with stretch n to the 1 plus epsilon. This is also an extensively studied assumption, starting with the sort of pioneering work of Goldreich and the work of Krein and Milterson in 2001. Again, also has been used in cryptography multiple times. And in fact, this assumption, this pseudorandomness assumption, in fact, also follows from a one-wayness conjecture, from assuming that a certain Goldreich one-way function is sub-exponentially hard to invert. That also implies the existence of these kinds of PRGs. That's due to this wonderful work of Applebaum et al. And then finally, we assume this so-called SXDH assumption over bilinear maps. Again, it's extensively studied assumption in cryptography, widely used since 2005 for a wide variety of cryptographic applications. I won't define it precisely just because we won't be using it. We won't be using any of the details of it. We'll just be using it essentially as a black box, using previous work that builds upon the SXDH assumption to build certain objects that we're going to be using that will finally be helpful to us to construct I/O. And with that, I would like to conclude part 1 of the tutorial. Please do stop me and ask questions before I hand it off to Rachel in part 2. Please let me know if there are any questions. Again, you can just interrupt. And just to give you I'm sorry, all the assumptions are made against sub-exponential time adversaries. Again, what we mean by that very precisely is 2 to the security parameter to the epsilon for an arbitrarily small constant epsilon, and a suitable security parameter for each of these assumptions. And just looking ahead, what Rachel will show us in part 2 is how to get to I/O, assuming a number of different intermediate objects. And she'll show us sort of how we use these objects to construct the I/O. And again, the linchpin there will be this new pseudorandom object called an SPRG, a structured seed PRG, which is this new pseudorandom object I was talking about. And then Aayush in part 3 will show us how to actually construct this SPRG, assuming PRG is an MC0 and the LPN over ZP assumption that I just talked about. And with that, I'll go ahead and conclude and hand over the talk to Rachel. And while I'm doing that, again, people can interrupt with questions if they have any. Let me go ahead and stop sharing. And Rachel, hopefully you can share.
Yeah, thank you, Amit. Yeah, I'm going to try to share, and you can answer questions at the meantime. Can people see the slides?
I think you shared you have to share the presentation view.
Yeah, definitely. I think just 1 second. Yeah, somehow the Zoom made all the videos like disappear. Okay, I guess I won't see anyone. I can do. Is this good?
Yes, I can hear it. I can see it.
Yeah, okay, good. All right, so then I will start. And thanks a lot to Amit for a great introduction. And I will continue with part 2 before Aayush. And for the purpose of the part 2, I think my main goal is to kind of explain how did IO, this very, very powerful object, get connected with this pseudorandom object. Well, pseudorandomness is not unfamiliar to us. It is one of the simplest or vanilla cryptographic tool, and they also exist in general theory and complexity. So how did this very powerful object about hiding programs get connected with pseudorandomness? Of course, with a lot of other powerful assumptions going on, but I hope that my part is going to convey to you how did this connection happen. Okay, great. So our goal is to construct IO from these 4 assumptions. And let's think about this task of constructing IO. Well, what we want in the case of hiding program is that I want to have a way to encode a program into an encoding that nobody can learn what's the program inside. But that's not it. Give me any input X. I would like to evaluate this input X on this encoded program that we don't know what the program is, and yet obtain the output in the clear. Okay, there are 2 challenges to this task. One challenge is that the computation for evaluating a particular input X could be very complex, and in particular, it can have very, very high degree. And the second is that we're not just satisfied in evaluating the input and obtaining the output in some form of encoding that nobody can decipher. In fact, we want the output in the clear. And these are the 2 great challenges we face when trying to construct IO. On the other end of the spectrum, what do we have? What can we do? Well, given that we have bilinear map, that Amit give you some intuition about what M-linear map is in general, and what bilinear map is really the simplest form of M-linear map. What it really allows us to do is to be able to encode certain secret values that I call S here, and then evaluating any degree 2 polynomial on the secret values and learn the outcome in the clear. So observing these 2 ends of the spectrum, what we want and what we have, we cannot help but noticing that there's a huge gap in the degree of the computation that we can handle. So how can we bridge the gap? A lot of the previous works actually showed that suppose we manage to have a very simple pseudorandom generator, how simple? It can be computed by just degree 2 polynomials. So this means that if the PRG has degree 2, then we can essentially compute it securely inside the bilinear map and learn the output of the PRG. With this pair together the bilinear map and the degree 2 PRG and lots of other crypto, then we can actually bridge the gap and obtain IO. Unfortunately, despite a lot of extensive effort trying to instantiate degree 2 PRG, it turns out that we don't have good candidates for it. It's not clear that whether we cannot have any candidates either, but at the moment, we don't know how to instantiate them. And the lowest degree that we can plausibly have sound candidate is degree 3. But on the other hand, we only have bilinear map, that we don't have trilinear map or degree 3 map that can evaluate those degree 3 PRGs. And hence we're kind of stuck in this conundrum. So what is new in this new pseudorandom object that Amit has been talking about is that essentially we can view it as walking on a very thin line in between degree 2 and degree 3 PRG, and we jokingly call it degree 2.5 PRGs. And at the same time, it turns out that we can also use bilinear map to raise a little bit what kind of computation can be done, can be evaluated on those secret encoded elements. And putting together, we can again instantiate the paradigm of going to the IO. Okay, so it's kind of mysterious that what is this degree 2.5? It doesn't make any sense. What we mean by degree 2.5 is this kind of computation, that the computation is on two parts of the input, or you can view it as a two-array function or two-array polynomial. One part of the input denoted as P is a public value. It does not need to be hidden. And the other part is the secret value, as we were thinking about before. And the polynomial that can be evaluated on them will be restricted to have only degree 2 on the secret value. However, can have the liberty to compute something more complex on the public part of the input. How complex? Any constant degree polynomial on the public input. This is what we call degree 2.5. And we can actually, using bilinear map, to safely evaluate polynomials of this form. And this is captured in this cryptographic tool we call partially hiding functional encryption. And we can actually build PRGs that have this public part of the seed and the secret part of the seed, and have computation that is only degree 2 in the secret part. And we call them structured seed PRGs. Adding them together with other crypto tricks, we can get IO. So, as I've already mentioned, that we can actually construct partially hiding functional encryption from bilinear maps. And in this work, for the first time, we show that how to instantiate this structured seed PRG using well-founded assumptions, in particular PRG in NC0 and the learning parity with noise over larger fields. An additional tool that you will see we're using is homomorphic encryption instantiated from learning with errors. And with these three intermediate tools that we built, we can construct a powerful primitive called functional encryption, albeit for some very simple functions at the beginning. But don't worry, we will be able to bootstrap functional encryption from these simple functions to all the way to functional encryption for computing all polynomial size circuits, which eventually will lead to IO. Okay, so this is a rather complex paradigm we're looking at. And what I will focus on in part 2 is just this middle part of how to construct functional encryption for NC0 from the intermediate objects we have. And then Aayush is going to later on tell you about how to build the structured seed PRG, which is the new primitive we construct. Okay, so in the rest of the talk, I will start to gradually build ideas for constructing functional encryption step by step. And along the way, I will introduce these intermediate objects such as partially hiding functional encryption and homomorphic encryption. And to start with, I will tell you about what is functional encryption and homomorphic encryption. And comparing them actually give us our initial ideas towards the construction. Okay, so any questions? Okay, because I don't see the other side, so if there are any questions, please just interrupt me verbally. Okay, so to tell you about functional encryption and homomorphic encryption, let's first quickly recap public key encryptions. They allow us to generate public and secret key pairs, and using the public key, we will be able to encrypt and input X into a ciphertext. And given the secret key, we can decrypt the ciphertext to recover the original input. So you can think about having the key allows us to open a black box hiding the input. However, the security guarantee is that without the secret key, then the ciphertext should really hide all possible information about the input X. So I'm going to use this notation with the parentheses of the input X appending to the ciphertext to kind of tell us that what is the input being encrypted. And sometimes I will also use subscript master secret key to denote what is the secret key involved for creating this ciphertext. But mind that the ciphertext hides information about the X and the master secret key, and this is just for notational convenience. And the security is formalized through this indistinguishability language, requiring that for any two messages, arbitrary messages, their ciphertext together with the master public key should really look the same to computationally bounded adversaries. And for the purpose of this talk, if you're not familiar with the language of indistinguishability, it's enough if you just stick with the intuition that ciphertext really reveals no information of the input X. Okay, so we can also sometimes consider secret key encryption, which is everything the same except that encryption, in addition to able to use in the master public key, can also use the master secret key to create the ciphertext. So homomorphic encryption, here we think about the secret key version, really extends the vanilla public key encryption or vanilla encryption scheme with this powerful capability to compute on the encrypted input without decrypting ever. So given any function f, we will be able to just transform a ciphertext of x into a ciphertext of the output f of x. And this is formalized through this homomorphic evaluation procedure that given the function and the ciphertext, without knowing the secret key at all, is able to transform a ciphertext that decrypts to f of x. Despite the fact that now we can actually do arbitrary computation on the encrypted input, without knowing the secret key, an adversary will still not be able to learn anything about the encrypted input. Why? Because all the ciphertexts they can create, inputs, outputs inside, they're all still hidden and no information ever revealed without the secret key. And this can again be formalized through the indistinguishability language. Well, homomorphic encryption is a powerful object. And here comes another one, which is functional encryption. Like a homomorphic encryption, it also allows us to evaluate computer computation on the encrypted input, but this time also learn the output of the computation. So how can we do that? Well, to learn some output of the computation, one needs to actually create what is called a crippled key that is associated with a function f. And this is done through a procedure called a key generation algorithm that takes the master secret key and the function and creates a specific crippled key tied to this function, so that when we decrypt using this special key, we do not learn what is the encrypted input, but rather learn the output of the function evaluated on the input. And with the secret key, the security, obviously one will be able to recover the output of the function, but the security goal is that that is only information that is revealed. And all other information about the input X that is beyond what can be inferred from the output must remain hidden. And to formalize this, we'll require that given two inputs, different input x0, x1, under the constraint that they are not separated by the output of the function, that is, they produce the same output, then their ciphertext, together with the master secret key and the secret key for function f, should be indistinguishable. Note that the restriction that x0, x1 have the same output is really necessary, because otherwise, just by the functionality provided by this tool, one can evaluate the output and distinguish ciphertext for inputs that have different outputs. So it turns out that functional encryption is extremely powerful, so powerful that it is almost equivalent to I/O. In fact, assuming LWE and PRG in C0, I/O is implied by functional encryption for even just very simple functions that belongs to NC0. And one requirement that we do have about the functional encryption is that it needs to be at least mildly efficient, that we refer to as being sublinearly compact, meaning that I require the size of the ciphertext should be linear in the output length, in the input length, and sublinear in the output length. And here, this notation O of lambda that I am using here is more or less the same as the big O notation, except that I also ignore polynomial factors in the security parameter lambda, because they are not very important for us. So why do we put this restriction that the ciphertext size needs to be sublinear in the output length? Well, note that we're considering that there is only a single secret key being published ever. And if we allow the ciphertext size to be as long as the output length, then one might well just publish the output. And we do not gain anything through publishing the ciphertext. However, if the ciphertext is sublinearly compact, then there is something to be gained, in particular, because the ciphertext size is actually smaller than the output length. Great. So functional encryption and homomorphic encryption are really powerful extensions of vanilla encryption schemes. And let's put them side by side and compare. Both of them enable computation over encrypted inputs. However, on the homomorphic encryption side, it still follows the classical all or nothing law in cryptography, in the sense that if an adversary if someone do not have the secret key, then really learns nothing about no information whatsoever. On the other hand, if a person gets hold of the almighty secret key, then all information is revealed. So it's either 0 or 1. There is nowhere in between. On the other hand, functional encryption is very different. And indeed, this all or nothing property is something that we cryptographers are rather good at achieving. And indeed, if we assume the standard learning with errors assumption, we can have homomorphic encryption for all possible polynomial-sized circuits. We can compute arbitrarily complex computation on encrypted data. On the other hand, functional encryption is rather different. Here it says that given a crippled secret key for function f, we will learn the output y, and that is only information revealed, or other information remains hidden. So this is pertaining to a very fine-grained control of what partial information can be revealed and what is hidden. On this front, we are rather kind of short in not knowing exactly how to achieve them. Essentially, the prior best known is using bilinear pairing to get functional encryption for only degree 2 polynomials. So the gap between these two objects is huge. Nevertheless, they bear quite some resemblance, especially in the fact that they both allow computation on encrypted inputs. So how can we construct functional encryption? One thought and a very natural desire is, okay, so why not just use homomorphic encryption to do the computation and then try to decrypt the final ciphertext that encrypts the output in a way that is secure and only reveal the output. If we can do that, then we immediately get functional encryption. But the question is, how can we actually decrypt the final ciphertext? The paradoxical idea that we're using here is that, okay, we don't have many tools that can allow this kind of partial revelation of information. So we have to use functional encryption itself for the decryption task. The hope is that this decryption task is simple enough that the needed functional encryption can be implemented easier. And in particular, if we can decrypt in just degree 2, then we're done. Okay, so let's start working with this idea of trying to bridge the gap between homomorphic encryption and the functional encryption. So in order to construct a functional encryption for NC0 circuit, we're going to create a ciphertext that contains a homomorphic encryption ciphertext. And we're just going to use the homomorphic encryption to encrypt the input. And using a key that is sampled fresh at the time fresh each time when we generate a ciphertext. Our desire is that then we can use a simpler functional encryption scheme and to include its ciphertext and secret key respectively in the ciphertext and secret key of the FE for NC0 we're building, so that when we decrypt the simple functional encryption, the output we get is exactly the output of the function f. Okay, so this is the rough template. The big question is, what are we going to encrypt and encode in the simple functional encryption to create the output of f? Well, let's try. One way we can do so is to, in fact, encrypt the homomorphic encryption ciphertext together with its secret key in the simple functional encryption. As such, then, the secret key for the functional encryption can be tied with a function h that first does the homomorphic evaluation to produce an output ciphertext that encrypts the output of f of x. And next, since h actually received the secret key for the homomorphic encryption as part of its input, we can simply use it to decrypt the output ciphertext, and that will produce the right desired output y. Okay, so that definitely satisfies our functionality. And if this simple FE is indeed secure, we will be having the guarantee that only y is revealed. The question is that we are hoping for some kind of bootstrapping, that this FE we need to use is indeed simple. In other words, the function it wants to evaluate is simple. But how simple is the function h? It turns out it's fairly complicated. First of all, that the homomorphic evaluation procedure cannot be simpler than evaluating the function f itself, because there is the computation of f happening homomorphically. Second is that the decryption of the homomorphic encryption scheme itself cannot be simple. In fact, we have lower bounds that decryption of any encryption scheme cannot be too simple. So this function h is rather complicated. It seems that this idea just goes nowhere. But however, it turns out that if we have the right tools, we can actually cope with the complexity of h. What are the tools? One is that we actually do have homomorphic encryption with almost linear decryption. Okay, I say almost here. The second is regarding the complexity of the homomorphic evaluation. the key observation is, well, though homomorphic evaluation is rather complex, note that it actually acts on the ciphertext, on HCT here, which does not need to be hidden. It's a public value. In fact, I can just give it away as part of the ciphertext in the clear. So this computation, though complex, however, is evaluated on some public input. Whereas the secret input that must be kept hidden is the secret key of the HE scheme S. And the computation on it is potentially simple, potentially almost linear. Well, the idea is that, well, shouldn't not only the complexity on the secret part of the input count? Well, whatever that's computed on the public part should not count as complexity. And indeed, this can be captured and achieved using this tool called partially hiding functional encryption. All right, so towards keeping developing the ideas, I will next tell you about these two tools and use them. We can move to further fleshing out the construction. Partially hiding functional encryption is very, very similar to the functional encryption that we have seen, except that now we're going to consider computation or functions each that have two parts of the input. One part of the input is public that does not need to be hidden, that's A here, and the other part is the secret part that we do care about hiding. So partially hiding a fee will allow us to generate a key for such two-array function, and at decryption time, as usual, it will produce the output of the function. Now, when it comes to security, what we want is that given the secret key, definitely one can learn the output of the computation, but also one can learn the public input. And the only thing that needs to be hidden is information about the secret input X that is beyond the output of the computation. And this is captured using a slightly different language, which we call the simulation security in cryptography. And it states that everything that is made public, the master public key, the ciphertext, and the secret key all together, they can actually be simulated or concocted using just the public input A and the output. Well, if that's the case, that these public key, secret key, and ciphertext can be produced knowing only the public input A and the output, then they must not reveal anything beyond A and the output. And this is the intuition for partially hiding functional encryption. It turns out that we can actually construct PHFE for degree 2.5 polynomials. So what are degree 2.5? There are these function h that can be expressed as a polynomial where each of the output element in this polynomial is actually degree 2 in the secret input x, and the coefficient or monomials of the secret input x are actually functions on the public input A, and these functions have only constant degree. So more accurately, I should depict the degree 2.5 as degree constant, comma 2, where the constant is the degree on the public input and 2 is the degree on the private input. So the constructions of partially hiding a fee for degree 2.5 polynomials uses pairing groups, and they do achieve the simulation security that we talked about. And furthermore, they're very efficient. The size of the ciphertext is in fact linear in the size of the input A and X. So as you see here that I have a little bit of a little star that is at the end, what I meant to capture is that there is a little caveat with respect to these schemes that correctness only hold if the output of the polynomial is small in the sense that the output has polynomial magnitude. So these polynomials each are evaluated over some finite field ZP, and P could actually be exponentially large. However, only when the output of H is polynomially small can the scheme correctly recover the output. Otherwise, it may not be able to recover the output. So this is the type of degree 2.5 computation that we can evaluate. And a slight note here is that in the talk, I am talking about the public key version of the partially hiding FE, but in the paper, we actually talk about the secret key version. And these details don't matter for the purpose of the talk. And in terms of result, it only means that it will change what is the assumption that we assume on the parent groups. Okay. So the other tool that we need is the homomorphic encryption. And in particular, a homomorphic encryption that has almost linear decryption. So how can the decryption be almost linear? We do know that decryption cannot be too simple. So let's investigate this front. These tools are built from the assumption called learning with errors. So recall that, as Amit have already told you, learning with errors is about observing a linear system, which without any noise is very easy to just solve. We can use Gaussian elimination. However, it becomes a lot harder as soon as we add some noise to these assumptions. What kind of noise do we add? We typically add small noise that are drawn from some Gaussian distribution, where small means that the magnitude of each noise element in the vector, each of them is polynomially bounded. And this is much, much smaller comparing with the modulus P. And in fact, all the other vectors and matrices, the A, the coefficient matrix here, and S, the secret vector here, are all much, much larger. They are random elements from ZP. Not only that, it should be hard to find the unknown secret S prime. The LWE assumption says that we cannot even distinguish these A and C away from just random elements that are completely sampled at random. So given this learning with errors assumption, we can easily hide information using it, right? So I'll note that for the assumption to hold, a very, very important element is that the unknown secret S and the noise must be hidden. If any part is made public, then one can again immediately solve the entire system. So how can we use LWE to hide information? This becomes super easy. If I have a bit string that I want to hide, all what I need to do is just to add it to the AS plus E part by the fact that the LWE sample is pseudorandom, indistinguishable from random. This means that adding X the C added with X will still be pseudorandom. One small detail that we need to take care of is that once we add X with E, X and E sort of blend together. If I want to recover information of X precisely, then I want to have a way to separate the noise from the message X. And this can be done by simply multiplying the noise with 2 to make the noise even. And it turns out that LWE still holds even if the noise is even. So as such, we see that LWE immediately gives us a secret key encryption scheme. Well, the C part is the ciphertext part. The A part can be viewed as the public key part. And the unknown secret S prime is the secret key. Note that this is a very efficient encryption because the ciphertext size is really linear in the input size. In addition, that from LWE, we know that the ciphertext is simply pseudorandom, and this definitely holds for one ciphertext. And the nice part is the decryption. The LWE is a highly linear structure, and in order to decrypt, all what we need to do is to kind of multiply S prime with the A and subtracted from the C part. In other words, it can be written as a matrix multiplication. And what it produces is 2 times E plus X. And this is almost linear decryption, because using just linear operation with the secret key, that we can actually recover the encrypted input, albeit that it's slightly perturbed by some noise. But nevertheless, that one can recover the input from the perturbed input by just doing a mod 2. This almost linear decryption equation, in fact, also immediately allows for homomorphic evaluation. So let's see how does this happen. So given any function f in NC0, we know that it is also computable by a degree D polynomial, some degree D polynomial over ZP. Why? Because a Boolean function is a multilinear, can be written as a multilinear polynomial where the degree corresponds to its locality. Given that f is an NC0 function, it do have small locality, and we just know this as D. How can I see evaluation, homomorphic evaluation? Well, a simple way to see it is that we simply want to evaluate the function f on both sides of the equation. Now, if I look at the right-hand side, f evaluated on 2e plus x equals to f evaluated on x itself, together with some term that sums up all the monomials that involve e. Given that each of those monomials actually involve e, and hence it must be even, I can simply summarize it as 2 times some new noise term e prime. In other words, this equals to 2 times e prime plus f of x. On the left-hand side, given that f is a degree D polynomial, we know that the left-hand side computation can always be made into a bilinear function on degree D monomials on A, C and S. So here I'm using this notation of a vector or a matrix tensor to D, meaning that this is the vector or the matrix tensoring itself D times, and naturally it contains all degree D monomials. And this means we can actually rewrite it into the form of a matrix CF multiplied with S tensor D. And the left-hand side and right-hand side equal give us this new, still almost linear decryption equation. The new ciphertext now is this CF, and it has a rather large dimension, which is M multiplied with the size of the secret S to the D. But as long as that the degree D is a constant, this dimension is still polynomial and trackable. And furthermore, the ciphertext can be homomorphically evaluated from A, C using just a degree D polynomial. The new secret key we have is this S tensor D, which is kind of expanded version of the old secret key. And what we get out of this almost linear decryption is again a perturbed output, where the output is perturbed by some noise that is a degree D polynomial evaluated from the original noise E and X. Given that the new noise is actually dependent on the old noise and the input X itself, this immediately tells us that we need to hide E prime. On the other hand, note that E prime is still small because it is a degree D polynomial on old noise and input. Both of them have small magnitudes. And this will actually be a saving grace for us later. Given that we have now these two powerful tools, one is a partially hiding FE that can evaluate degree 2.5 computation, and the other is a homomorphic encryption that has almost linear decryption. Let's plug it into our paradigm and see how the scheme looks like. Well, now the ciphertext of HE looks like AS prime plus 2E plus X. And we're actually going to include the public A into the master public key, and the secret S prime is sampled fresh each time a ciphertext is generated. Now we can encrypt the homomorphic encryption ciphertext and its expanded secret key using the partially hiding functional encryption. And what function do we want to evaluate? What should H be for us to recover the output Y, which is an f of x? Well, like before, H is going to homomorphically evaluate the function f on the ciphertext and obtain CF, which is this rather big matrix that we saw in the previous slide. And now the neat part is that decryption can be done by simply multiplying CF with the expanded secret key, and it will produce a perturbed output. The great news is that now we have managed to curb down the complexity of H. Why? Because the degree of the homomorphic evaluation is constant and evaluates on the public input, the ciphertext. And the degree of the secret part of the computation is in fact just linear, because the homomorphic encryption has almost linear decryption. We also have compactness. The size of the ciphertext is not too large, because the only part that could be large is this expanded secret key, but that does not depend on the output length at all. It's in fact a fixed polynomial in the security parameter. So all seems to be good except for one security bug. That is, this function H does not give us Y alone. It actually gives us the perturbed output, Y plus the noise. And as we mentioned, this noise E prime actually depends on the input and the original noise itself, and it will completely reveal information of X, which we want to hide. All right, so how can we cope with it? Well, we cannot do mod 2 to attempt to get rid of the noise, because mod 2, though simple, it's still an NC1 function that does not fit into this simple function H that we want to have. So the saving grace is really the fact that we observed before. The new noise in the output is still bounded by some polynomial. It's rather small. So a different way to hide the small noise is by adding an even bigger noise to it, so that the information about the small noise gets flooded by the big noise. Indeed, if we make sure that the magnitude of the new noise rho is reasonably big, then we can be sure that the statistical distance between rho plus E prime is actually very close to just rho itself. This means that we do have some security because E prime is partially hidden by this larger smudge noise rho. We're partially hidden, I mean that we can more or less think about that it is hidden with probability 1 minus 1 over lambda, but there's still a tiny 1 over lambda probability that E prime is not hidden. On the other hand, that correctness still holds, because recall that we're using the partially hiding functional encryption to compute this perturbed output. And correctness only holds when this whole thing is polynomially bounded. But this is indeed the case because we set up the smudge noise to be relatively larger than E prime itself, but still polynomially bounded. Great. This means that instead of just straightforwardly decrypting the output ciphertext CF, we now want to also add some additional smudge noise 2 times rho. Question is, where does the rho come from, right? The most straightforward idea is to just supply rho inside the ciphertext of the partially hiding FE, so that my function H now can actually take rho as the input and add it in the secret part of the computation. Well, this still gives me a very simple H because all we're doing is addition. And security now is partially restored because E prime is partially hidden. But the problem is that row itself is just too long. The length of row is as long as the length of the output. And that would mean my ciphertext now becomes as long as the output, and it totally kills compactness. So this idea does not work, and that's why we need pseudorandomness. The next very natural idea is to try to generate row using a pseudorandom generator so that we only need to encode seed that is much shorter than row itself. And yet the seed can be expanded to generate the much longer row. Well, now we understand why we need pseudorandomness. And we also understand why we are in need of extremely simple pseudorandom generators. Why? Because the whole thing needs to be computed inside my simple function H. And in fact, we would like it to have very, very small degree in the secret seed itself. This naturally leads us to come to the structured seed PRG, and which is the final tool that will enable the construction. So to quickly recap, what is a PRG? Well, it is an expanding function that will allow us to expand a seed, which is a binary string, into an output that is a binary string, which is polynomially longer than the seed. Here, we just think about the size of the seed, which is sublinear in the output length with the exponent 0.99, but 0.99 could be arbitrary constant smaller than 1. We often consider a family of PRGs, meaning that there is a function, there is a distribution of the index, and there is a distribution of the seed, so that the evaluation of the PRG takes the index and the seed and produces the output. In other words, the PRG function can be viewed as the evaluation with a particular index hard-coded in. Well, what should we think about? We should just think about that this index is some public parameter that is hard-coded in the PRG. And we want indistinguishability in the sense that given the public function index and the output should be indistinguishable from purely random strings. And when we talk about simplicity, the simplicity we need here is the evaluation or the PRG computation can be done by a low degree polynomial over the Boolean cube. And over the years that the quest for such a simple PRG has went on for quite some time, what do we know? What we know is that we can actually have a Goldreich PRG, which is in NC0, also implies that they can be evaluated by constant degree polynomials. But below constant degree, how small can we drive the degree to? Despite a lot of effort, so far we have no candidates for degree 2 PRGs. Linear PRGs do not exist because linear functions we can simply solve to find the C. Degree 2, there is still some hope, but we don't have good candidates for at the moment, which is still a great open question. Yet, we cannot cope with degree 3 PRG in our construction. So the question now is, can we have just slightly more powerful PRG, degree 2.5? So we formalize them as structured seed PRGs. What it means is that now the seed actually consists of two parts, the public seed part and the private seed part, denoted as P and S respectively. And security now says that the output of the PRG should be pseudorandom, even given the public seed. So in other words, the public seed does not hurt the pseudorandom property. And now we can consider PRG that are just slightly more complex. In particular, it can have the constant degree on the public part, but restricted to have only degree 2 in the private part. We might be wondering that why is the public part helping at all? Like, why is it useful? Given that it's public, isn't that it's just reusable? For example, why doesn't it just collapse down to a normal degree 2 PRG? The reason that it doesn't collapse down to a normal degree 2 PRG is because that the public and secret seeds are sampled jointly together, and they can be arbitrarily correlated, very complexly correlated. As such, even though the public seed is made public, it's actually not reusable, because given the public seed, it could be computationally hard to conditionally sample the corresponding private seed. And this is why it is more powerful than just a degree 2 PRG. And previous efforts towards constructing such structured seed PRGs all had to rely on some new assumptions. And in this work that we built the first time, this tool from well-founded assumption, namely learning parity with noise over large field and PRG in NC0. And just heads up, we actually don't manage to build a full-fledged structured seed PRG, but rather a weak version. But for now, let's assume that we have an ideal version, and I will tell you later that how does the weakness come in. Given our final tool of this structured seed PRG, we can now complete the construction. Naturally, we're going to encode the seed of the PRG in the ciphertext of the partially hiding FE. Now the public part belongs to the public part of the input, and the secret seed belongs to the secret part of the input. As such, that now the function little h can inside evaluate the PRG on the public and the private seed to generate the pseudorandom, a very, very long pseudorandom string R. And using R, it can put different bits of R together by multiplying with powers of 2 and adding them together to form these much larger smudge noise rho I that are still polynomially bounded. And finally adding those larger smudge noise to the perturbed output in order to hide the output noise E prime. Let's see that H is still degree 2.5, just as we wanted. The public part of the computation consists of the homomorphic evaluation, which has constant degree, as well as evaluation of the SPRG, the part on the public seed, and it still has constant degree. The private part of the computation consists of evaluation, the secret part of the SPRG, which has degree 2 on the secret seed, and a bunch of linear operations following that, involving decryption and adding the smudging noise. And hence the whole thing actually do have degree 2.5. We also have compactness thanks to the polynomial stretch of the PRG. Note that the new part being encoded in the ciphertext is the seed of the PRG, but because it's a PRG, the seed length is sublinear in the length of the output, and this gives us sublinear compactness. So let's finally pay attention to the security. What we want out of security is that from what is observed in the public, which includes the master public key, the secret key of the FE scheme, which consists of a secret key of the partially hiding FE, and the ciphertext, which consists of the ciphertext of the partially hiding FE, and also the homomorphic encryption ciphertext that we are not trying to hide. All of this information together should only reveal the output of the function y and nothing about the input x beyond what is revealed in the output y. And this is what we're going to prove. Namely, given any two input that have the same output y, all these variables that are published about them, the master public key, secret key, and ciphertext, should look indistinguishable. And this indistinguishability tells us that only information that is revealed is Y, and what's beyond that is hidden. We won't be able to actually prove the full-fledged indistinguishability, but rather only a weak version, in the sense that these two distributions corresponding to x0 and x1 are not negligibly close, not very, very close. However, there is some distinguishing gap that one can actually distinguish them with a difference of 1/λ in probability. And this is what we call weak indistinguishability security. So let's see, how does the proof proceed? Let's start with thinking about one distribution, any one, that is encoding either x0 or x1 that we denote as xb here. To start with, we know that the public key, secret key, and the ciphertext are generated using partially hiding FE, which give us the promise that the only information leaked from them is the output of the partially hiding FE and nothing else. And in fact, this is captured strongly by the fact that these variables can be simulated or concocted using just the output itself. And the output here is exactly the perturbed output plus 2 times rho, where rho is generated using the structure seed PRG. And these two distributions are indistinguishable by the security of partially hiding FE. Next, observe that our SPRG give us outputs that are pseudorandom. Therefore, the rho generated from SPRG is indistinguishable from some rho prime that is purely random. And these two distributions are indistinguishable following from the security of SPRG. And at this point, remember that when a relatively small noise is being hidden by a much bigger noise with the right parameters, the statistical distance between E prime plus rho prime and the rho prime itself is bounded by 1/λ. And this means that this distribution is now very close to the other distribution where E prime just magically disappear. Okay, these two distributions are not very, very close. There is a chance of 1/λ that they can be distinguished, but this is still big progress. All right, now that at this point, we can notice that nothing about the homomorphic encryption ciphertext, no secrets of the homomorphic encryption ciphertext is revealed, right? The secret key is not revealed, the noise is not leaked, and hence simply by the security of the homomorphic encryption, the encryption of input XB is indistinguishable from an encryption of simply 0. And this lands us in this final distribution, and observe that the final distribution has nothing to do with what is the input that was originally encrypted. X0, X1, both distributions were being distinguishable to this common distribution, and as such, we can conclude that these two distributions for X0 and X1 are indistinguishable. Okay, so I did mention that we actually don't achieve full-fledged structure seed PRG, and rather only a weak version. The weakness comes from the fact that the output of the SPRG is not negligibly indistinguishable from purely random strings, but rather again, it actually has a small distinguishing chance, which is of order 1/λ. But as you can see that in our security proof, we already have a weak indistinguishability of 1/λ going on. Therefore, it doesn't really change the statement in the end. As such, we have obtained functional encryption for computing NC0 functions, albeit that it only satisfies a weak version of the security. To compensate for the weak version of the security, we observe that the bootstrapping of FE for simple functions to FE for all polynomial-sized circuits actually still go through, and we will be able to obtain a weak version of the FE for polynomial-sized circuits. And then we can actually apply a security amplification step to boost the security back to the level that we want, and hence then it will allow to imply I/O following previous work. And with the remaining time that I will try to, how much time do I have?
Well, let's see. So we have each part running for about an hour. I think we started 30 minutes late, right? Amit?
Yeah, I think I can maybe skip this part and just Aayush can take over, given that we are a bit late.
So Rachel, if you want to move on to part 3,
Yes.
in about 5 minutes or 10 minutes, I think we'll be in good shape.
Okay. Okay, then in 5 minutes, I can just give you some rough idea about the security amplification, and we can move on. Thank you, Sasha.
Thanks.
Okay, so I just want to give you a teeny bit of the idea of how security amplification works and what kind of very fascinating crypto tools that goes into it. And this part is not going to be very detailed, so it's just some intuitions. So security amplification, in fact, is a big question in cryptography in general, and it also applies just for basic vanilla encryption scheme. So we can think about if I were given with an encryption scheme that is only somewhat secure, let's say delta secure, and we can think about it in a loose fashion that delta secure means that it's sometimes secure, sometimes not secure with some good probability. Then how can I actually boost the security up to be fully secure? Well, the basic idea is that I can actually run this loosely secure encryption scheme multiple times, generate lots of instances using completely independent master public keys, and with some good probability that one of the instances is going to remain secure. And it's actually not quite easy. The intuition is easy, but the math behind is rather deep, and it is the famous hardcore lemma. But given the fact that one of the instances is going to remain secure, we can now, and all the other instances may be completely broken, and hence what's encrypted inside will be public. We can securely, safely hide an input X by first secretly sharing it into lots of different shares that have the guarantee that if one collects all the shares, then the input X will be revealed. However, as soon as one of the shares is hidden, the input X remains hidden. And building such secret shares is well known in cryptography, and this gives us a way to boost back the security of a vanilla public key encryption. The difficulty that we face with the functional encryption is that it also wants to compute on the inputs. So this would translate to doing some computation on the shares. And indeed that we can actually build an advanced type of secret sharing, that a secret can be decomposed into lots of shares. And in addition, given any input, given any function f, we can actually evaluate the function on each of the shares independently without any coordination. It's just evaluating on each individual shares. And that produces a share of the output. From the shares of the output, one can reconstruct the actual output itself. And the security guarantee is similar to a vanilla secret key encryption scheme. What we want is that as long as one of the input share for the input X remains hidden, and even if everything else is made public, or the other shares are made public, or the output shares are made public, the only information that is revealed from there is the output Y, which can be constructed from the output shares, but no other information of the input X is revealed. So with this type of advanced secret sharing, we can now boost the security of functional encryption. How? We're going to share the input X into the shares and encrypt them using independent instance of the weakly secure functional encryption scheme. And for each of the weakly secure FE instance, we can publish a secret key corresponding to evaluation on the shares. And decryption on each of the share, each of the instance will give me one output share. And from it, we can reconstruct to get the original output. Now, as long as one of the instance of the weakly secure FE turns out to be secure, it will give me the guarantee that only the output share in that instance is revealed and the input share is actually hidden. And therefore, the security of the advanced secret key sharing kicks in and guaranteeing that only the output is revealed and not the input. And this is sort of the rough intuition. To really work out the details, we do have to overcome a couple of challenges, but they can be done. And this is kind of the intuition behind how we can do security amplification. And this sort of hopefully give you a picture of how to construct I/O from these intermediate objects and what those intermediate objects are. And the remaining important piece is how we can actually build this PRG that have degree 2.5 from the well-founded assumptions. And with this, I'll hand the baton to Aayush.
Thank you, Rachel.
Maybe I can start sharing my screen.
Yes, let me figure out how do I stop sharing.
Before that, I have a question.
Yes, please.
Okay, but I need your slides to ask the question. So in the part where you did like the homomorphic encryption for F, sorry, it would be helpful if you have the slides.
Oh, okay. Let me stop sharing. Rachel, can you try?
Okay. Somehow the sun is really on my face and I can barely see anything on my screen. I think this is it. Yeah. Homomorphic encryption of F. And can you tell me that which slide I should go to?
The one where you write F as a polynomial over ZP.
This one?
Yeah. So here I got confused by this. So F is a Boolean function, right?
Yes.
Computable in 0. So does that imply that it's a small polynomial over ZP? Because here P is not 2, right? You'll have P can be some arbitrary.
Yeah, P is not 2. Yes, so F is a Boolean function, but it is NC0. So each of the output elements in F is computed by a NC0 circuit. And we know that this Boolean function can have multilinear degree that is equal, at most multilinear degree of its locality. And because it's an NC0 function, the locality is a constant. So you can think about the degree D here is really the locality of this NC0 function.
Okay, so that D is independent of P.
D is independent of P, yes, very much so. The important part is that we are only, this polynomial, degree D polynomial, only need to compute F over the Boolean cube, right? So if I, like, given that F only depends on D input bits, whatever polynomial, even if you think about a very high degree polynomial evaluated on D input bits, because if X is a bit, X squared actually equals to X. So it will collapse down to a multilinear polynomial.
Right.
And if it's multilinear and only depends on D input bits, the degree cannot be bigger than D.
Right.
Yeah, that's the transformation.
So when you write f of x plus 2a in the next or in the previous, I don't know, in the next slide, so you're actually now extending this f not just as a Boolean function, but now you're looking at it as a polynomial.
Yes,
When you write f
yes,
of 2e plus x, okay, such that the restriction on the Boolean hypercube is the function.
yes, yes.
Okay,
So I'm
okay.
viewing f both as the NC0 function, but also as a degree D polynomial over ZP. And the degree D polynomial computes f over the Boolean cube.
Okay, yeah, thanks. That this is switch kind of confusing.
Yeah, the switch, sorry, I should have explained more detail, yeah. Thanks for the question.
So is this visible somewhat?
Yes.
My screen? Okay. Oh, wait. Okay. Okay, so let me, so welcome to the third part of this tutorial on constructing indistinguishability obfuscation from well-founded assumptions. But before I proceed, I just really want to give a big shout out to the organizers and Sasha for giving us an opportunity to present our work. And I want to thank both of my amazing collaborators, Rachel and Amit, who gave the second part and the first part of this tutorial. So let me now recall from what you saw in part 2 and part 1, namely this picture. And Rachel did a fantastic job in explaining the kind of laying out the overall chart of how to construct indistinguishability obfuscation from these 4 assumptions. So just to recall, she said that in order to construct IO, it suffices to build what is known as weakly secure functional encryption for NC0. And then she told us that to build this notion of weakly secure functional encryption of NC0, it suffices somehow to build 3 simpler cryptographic primitives. First one is the notion of partially hiding functional encryption that you can build from standard assumptions on bilinear maps. Then there's another notion, homomorphic encryption for NC0, that you can instantiate from LWE. Then really the missing piece of this picture is a pseudorandom generator. It's a special pseudorandom generator, which we are calling structured seed PRG. And in this talk, I'm going to tell you how we can build this weakly secure structured seed PRG, assuming 2 assumptions, PRGs in NC0 and LPN. And once you have that, then we can plug it in this picture, and this will complete this chart, and we'll have IO from these 4 assumptions. Okay, so for the rest of this talk, my goal is just to focus on this structured seed PRG, and I'll try to give all the technical details that you need in order to build that. And hopefully that will be enough. Even if you forgot the details in part 1 and part 2, this talk will be sufficiently self-contained, and hopefully you should be able to follow. And if you have any questions, please stop me at any time, because that will also help me to figure out if I'm losing any of you. Okay, so now I'm going to present my details, and so it will have some equations, but hopefully they are friendly and trivial, so do not get intimidated by those equations. Okay, so just to summarize, in this part, I'm going to tell you how to construct this object structured seed PRG from 2 standard assumptions: learning parity with noise over large fields, and existence of Boolean PRGs in NC0 with polynomial stretch, and that will complete the picture. So now I'm going to recall both of these assumptions with an aim to kind of remind you what those assumptions are, but it will also help us to set up the notations for this talk. So the first assumption is that of learning parity with noise. What does it say? It talks about indistinguishability of 2 distributions. The first distribution looks like this. You're going to have coefficient vectors AI, which are chosen at random from a field ZP to the power L. So it's a vector of L dimension over ZP. Throughout this talk, think about P as being the order of the bilinear group. So it's some sub-exponential. So you're going to sample those coefficient vectors. And then you're going to give out noisy linear equations. So you're going to sample a secret S from ZP to the L. Then you're going to compute this inner product. Okay, and then you're going to add it with some noise. Now, this noise is a sparse noise. So it's 0 with a large probability, But with probability L to the minus delta, where L is the dimension and delta is some constant, I'm going to choose it at random. So the delta sits in, it's a constant between 0 and 1. So I'm going to choose this error with probability L minus delta to be random, and then I'm going to add it and do modulo P. So I have these noisy linear equations. How many noisy linear equations I'm giving out? I'm giving out n, which is some polynomial in L. And now the goal is to distinguish this with a tuple which looks like this, which has coefficient vectors ai. And instead of noisy linear equation, now I'm going to generate some uniformly random samples from ZP and give this out. So that's the LPN assumption. The assumption says that these two are indistinguishable. Now, what do I mean by indistinguishability? I mean that they should be hard to distinguish for sub-exponential size circuits. By that, I mean that there exist some sub-exponential size bound such that for any adversary of size less than that, these two distributions are hard to tell apart. Another question that arises is, what is the parameter delta that I'm using? What is the probability of error? So for our work, we can work with arbitrarily small constant delta. So delta can be greater than 0, a constant that can be arbitrarily small. So even if this assumption holds for delta equal to 0.0001, that's already enough for us to build IO. And just to give a perspective, in the first part of this talk, Amit detailed, actually in a quite bit of detail, he told us about the relevance of this parameter. If delta is made close to 1, that means the probability of error is very small. So in fact, if it's 1, then it's polynomial time broken. When delta is close to 0, then this probability of error becomes large, and therefore the problem becomes hard, and therefore we are asking a very modest amount of it's a fairly modest setting of parameter. We are asking delta to be an arbitrarily small constant greater than 0. I'm going to skip on the perspective and historical significance. Amit, if you want to look at it, just go back to the first part of the tutorial. But just I want to also make one point. For those of you who are familiar with what LWE assumption is, and this is also an assumption that we are using, this syntactically looks very much close to like LWE. The main difference is the error. In LWE, the error was sampled from bounded discrete Gaussian. Here we are choosing this error to be a sparsely chosen field element. So that's about LPN. Then I'm going to recall one more assumption, which I'm going to use. Boolean PRGs in NC0. What are Boolean PRGs? Well, they're nothing but they're length expanding Boolean functions. So what do? They take n bits of input and they output m bits. So they expand. This m is, think of it as some polynomial in n, for example, n to the 1 plus some constant. And we are looking for such functions in NC0, meaning that they are computable by constant depth Boolean circuits. Okay, and they satisfy a security property, which is the standard cryptographic security that you hear all the time. What does it say? It says that when I sample the input x or the seed at random from 0, 1 to the n, this output g of x looks computationally indistinguishable to a random string of length m. Okay, so that's just cryptographic pseudo-randomness. And this indistinguishability, again, is the same kind of indistinguishability that I was referring to the previous slide, sub-exponential indistinguishability. So that's the assumption we are making. Now there are a few facts that I want to just remind, because I'm going to use these two facts later on in this talk. So it's just good to keep it in the back of our mind. So there are two facts that are nothing to do with PRGs per se, but they are more related to Boolean functions in NC0. And therefore, they also apply to our assumption. So the first fact is that for any Boolean function in NC0, the locality is a constant. So what do I mean? I mean that every output bit can only depend on a constant number of input bits in X. Okay, so that's what locality means. An immediate corollary of this fact is that if you try to write each output bit as a polynomial over the reals on X, then the polynomial that you get, there exists a multivariate polynomial which has a constant degree, and it has integer coefficients. Okay, so just let me repeat. Every output bit can be written as a polynomial in X over the reals with constant degree and integer coefficients. So that's just from the multilinear representation of Boolean functions in NC0. And these are the two facts that we will use later on this talk. So if you have any questions about them, please ask me at this point. Sounds good. So just to give you a sense of what parameters we are using a stretch of n to the 1 plus tau for an arbitrarily small constant tau greater than 0. So even if this assumption holds, even if there exists a PRG in NC0 with a stretch of n to the 1.0001, that's sufficient for us to build IO. So that's kind of the main claim. So this was about PRGs in NC0, and Amit also gave a perspective and history about this in this tutorial. So throughout the first two talks, we were talking about structured seed PRGs, and so now I want to understand what is the real structure and why is it so useful for us. And Rachel talked about this in great detail, but just let me summarize again. So the main idea is that we are looking for PRGs which are actually bilinear map friendly. So they are implementable by bilinear maps. What do I mean by that? So I'm going to give you a real informal definition. The formal definition you saw in Rachel's tutorial, but also I will tell you later when I absolutely need it. But roughly the main intuition is that each output bit of the PRG is computable by some degree 2 polynomial modulo p. So on ZP, it's some degree 2 polynomial on the input, where the coefficients are some field elements. Okay, so that's kind of the structure that we need. They should be implementable by using bilinear maps. So each yi is a degree 2 polynomial over ZP, where P is the order of the bilinear group. Throughout, when I say P, it's the order of the bilinear group. So those are the kind of PRGs we are trying to find out. Now, this is not new to our work. We are not the first work which observes a connection between PRGs with this low evaluation complexity to IO. In fact, before our work, there were several other works, starting from the work of Lin and Tesaro until our work, where there's kind of a pseudo theorem that has been established, and it's like a template where if you have some bilinear map friendly PRG satisfying some properties, then along with standard assumptions, typically you can construct IO. So it's kind of a pseudo theorem that's kind of established. And what we do in this work is that we come up with a bilinear map friendly PRG from two well-established assumptions, PRGs in NC0 and the LPN assumption. So that's kind of the overall picture. So now I'm going to do a slight detour. I'm going to do a little bit of history and how these bilinear map friendly PRGs evolved over last few years. And what's so nice about this evolution is that we had a amazing feedback from sum of squares and the algorithms community, which helped us to constantly refine these notions of PRGs and helped us immensely to build SPRG. And this evolution will also help us a lot actually to build us slowly towards our solution. So there are two aims in covering this. One is to just talk about the history. The other is to show you the gradual progression in terms of building our solution. So the first notion of these bilinear map friendly PRG were known as degree 2 PRGs, which came in several works. And again, they are in two kinds. First ones were called as Boolean degree 2 PRGs, which were proposed in the work of Lin and Tesaro. There, the input sits in a Boolean hypercube, and the output is also a Boolean hypercube. It's also a Boolean output. Then after that, another set of degree 2 PRGs came, which were integer degree 2 PRGs, where the input actually sat in, it was a vector in integer. So let's say they were sampled from minus lambda comma lambda to the end, where lambda is some parameter. And the output was also an integer. But really what was the unifying feature, and as the name suggests, degree 2 PRGs, their evaluation was really simple. In each of these, the main point was that the output is some degree 2 polynomial over the input where this polynomial is computed over the reals, and the coefficients are some distributions of over z. I don't want to get into all that, but this was the structure. And now, as you can imagine, this is all trivially, you can think of it being implemented by bilinear maps. And all these works here, they showed that using such PRGs and some standard assumptions, you can build IO. So that was the main intuition. But unfortunately, as you can, if some of you who are from algorithms community, you can already see that such a simple structure would already make you suspicious. And indeed, that was the case. It was subject to devastating set of implausibility results. So major culprit in all those results was this powerful hierarchy of convex optimization called sum of squares hierarchy. And some of the best known approximation algorithms for really hard problems are instance of sum of squares hierarchy, such as even the max-cut, the Gomez-Williamson algorithm. That is an instance of sum of squares. So that was the major culprit. And the main idea behind this implausibility, so if you look at the Boolean versions of the degree 2 PRGs, they were shown to be implausible by Barak et al. And Lombardi and Vaikunathn, who showed they used a really powerful inequality, which is a fallout of sum of squares, the symmetric version of Grothendieck inequality. And they showed that that inequality can lead to implausibility against wide generality of such PRG predicates. Then, when it came to integer PRGs, a work involving me with Boaz, Sam Hopkins, Pravesh, and Amit, we showed that the algorithms that are typically used in matrix sensing and matrix completion, such as the nuclear norm minimization, that can already rule out a very general class of integer PRGs. So the key takeaway from these implausibility results was that although they are not impossibility, they don't rule out all the parameters and all the types of constructions. The main takeaway was that you don't want to construct a PRG where the evaluation is a degree 2 polynomial over the reals, because of these implausibility, there was like the overall confidence about these assumptions were shaken. And to date, we do not know of any candidate PRGs that exist that doesn't bypass these attacks. So although it's not an implausibility, it was still a major blow. And the main takeaway was that you want to not rely on PRGs where the computation is a degree 2 polynomial over the reals. But now this might already sound like a roadblock. Why? Because I kept telling you that, okay, we need to construct PRGs which are implementable by degree 2 multilinear polynomials over ZP. And I'm telling you that this avenue is blocked. Like, you don't want to construct PRGs with degree 2 computation over the reals. So really, there's a very tiny gap between these two models. And the question is, can you escape this implausibility and leverage like bypass this implausibility and construct something which is implementable by bilinear maps? So that was the goal. And turns out that main turning point, one of the main key ideas came in this notion of degree 2.5 integer PRGs, which came in my work with Amit and Prabhanjan and Rachel and Christian Matt, where it's a PRG which escapes this implausibility. So let me tell you in detail how they look. So your input is going to be an integer vector. It's in minus lambda comma lambda to the n. Okay, so it's an integer. And your output is going to be a polynomial. Okay, so a polynomial with degree greater than 2. So in fact, it will have the degree greater than equal to 3. So it's good because it's no longer degree 2 and escapes those attacks. So it's going to be a polynomial of degree greater than equal to 3. So that's the PRG component. But then we showed that this you cannot quite compute. You'll have to compromise a little bit. You'll have to pay a price. The price comes in form of a leakage, which looks like this. So let me parse this leakage. Your input is going to be a vector of n dimension from minus lambda comma lambda to the n. And your leakage will have exactly n LW samples. So if the length of the input was n, you're going to have exactly n LW samples, where each LW sample looks like AI inner product S plus EI modulo P. So this mod P computation is over the bilinear map. What I mean is that this order P is the bilinear map order, and you're just adding, you're just having n LW samples where the error is exactly equal to the input coordinate. So it's a leakage on the input of the PRG itself. Okay, so that was the leakage that we had to give out. Now there are two questions that arises. Why is it helpful and is it broken? So let's look at why is it helpful. So the point was that if I did not give out this leakage and I wanted to compute it using Balinear maps, then of course I cannot compute it using Balinear maps. The reason is simple. It's just a degree D greater than or equal to 3 computation. It's not a degree 2 computation. So there's no way I can compute it using Balinear maps. But the point is, once I give this leakage, then I can devise a short seed, okay, which depends on the secret of the LW samples. I can devise some seed such that now I can write these polynomials as some degree 2 polynomials over this new short seed, where the coefficients of those polynomials might depend on this in a simple fashion. Okay, so that was the main idea. The main idea is that once I have this leakage, I can devise a new seed such that I can write this as a degree 2 polynomial over the short seed, where the coefficients might depend on this. And Rachel did motivate this in her talk and told you the exact models and all that. I'm going to recall all of that later in this talk. So even if you missed that part, that's completely fine. So that's why this is useful. Now let me talk about give you a story, and then I'll talk to you about why this is not broken. So the story is that if you observe carefully, I'm putting degree 2.5 in double quotes, and that's what Rachel also did. These are in double quotes because that's not a formal name. It's an informal name that community accepted. And why are they called degree 2.5 PRGs? Well, the main reason is that if you did not have this leakage, then I would have called it degree 3 PRGs because they are degree 3 and up. But since there is leakage, so they are not degree 3. Okay. But they are not degree 2 either. So that's why it was called degree 2.5, and it was accepted really well in the community. Now, before I proceed, I just want to ask if there are any questions. This will be a good time. Are there any questions?
So what exactly does it mean that it's a leakage? Like, isn't that kind of like an input of sorts? Like you're using this to, like your Q depends on this LW leakage, right?
Right. The Q will depend on the LW leakage. So yeah, essentially it's good in the actual scheme of things. In the bigger set of PRG, this will be part of the input, but this will be the public part of the input. This will be revealed to the adversary. That's what I'm trying to say.
Okay. And so is this E is not this EI? It's not a function of this EI. This is a different E. Like this was
this E.
Yeah.
This E is exactly equal to the ith component. So E vector has E1 through En, and
Right.
this error is exactly equal to the ith component.
Oh, this is exactly the same. But
Yeah,
then isn't that in ZP to the M then?
What is in
this QI? So then if this E and this E are the same, then how do you get
right?
Like
First of all, they are LWE errors, right?
Mm-hmm.
So they are small. They are not big. They are not ZP element. They are rather integers. These EIs, right? They're polynomially sized because this is an LWE sample. Like each E is sampled from bound minus lambda comma lambda to the n.
Oh, okay. It's not the
Yeah,
LPM.
and this is a degree 3 polynomial over the reals, degree 3 or up.
Okay, and
so
we must think of this P as fixed throughout the thing, like P is some fixed thing.
P is the order of the Balinear map.
And what do you mean by that exactly? Like,
so in the other part of the scheme, we are using a Balinear map which has an order P. So
like some group with order P on which you
yeah,
have
it's a group with order P.
Okay.
We are using in the other part of the protocol, and this will use the same P. That's what I'm saying.
Okay.
Right.
Okay.
So just let me summarize again. You have in this, just let me recall the structure again. Your input is going to be an integer vector from minus lambda comma lambda to the n. So it's bounded. Now there are n components in this input, right? It's n dimensional. So I'm going to give out n LW samples. where ith LW sample will use the component EI, and along with that there'll be the actual PRG part, which will be some degree 3 polynomials, randomly chosen degree 3 polynomials from some distribution, but they are over the reals, these polynomials. Okay, and the claim is that once I have this, then I can pre-process a new seed, which depends on the secret of the LW sample, such that lets me compute these polynomials as a degree 2 function over this new seed, degree 2 over ZP. As a ZP polynomial, it will be degree 2 polynomial over this thing, where the coefficient of those polynomials will depend on this in a simple manner. That's the idea. Okay, so why were they not broken? Well, if you remember, the implausibility results came due to sum of squares hierarchy. It turns out in this case, if you just ignore the LWE leakage, then we can actually show that you can provably resist these kinds of SOS algorithms in the form of an SOS lower bound, which is allowed to even run in sub-exponential time. So we have such SOS lower bounds, so that's nice. And so far, actually, there are no other attacks known. Any attack which runs in, I mean, the best known attacks are sub-exponential. So there are no other attacks known, and it's still an open problem if you can break such degree 2.5 integer PRGs. Right. So this was good, but the fact that there are no attacks and we were able to systematically design a PRG which escapes such attacks, that was nice, but it was still unsatisfying. And the main reason why it was unsatisfying is that there was an unusual leakage on the PRG input. Okay, so just if you recall, this was the structure, this is the PRG, then I have a leakage in which the error is exactly the input of this PRG, right? So this was an unusual leakage. And if you look at these parts independently, if you just look at the LW sample, this is fine because due to LW security, this is nice. If you just look at these degree 3 polynomials, they are also nice because probably they are solid in the sense that there are no SOS algorithms and those kind of things. So this is also nice independently, but the fact that you have an error which is reused in both the things, that was the main issue, and there was no way we could think of where you can separate these two assumptions out and kind of argue security. That was where we were stuck. And this brings us to the main contribution of our work. What we do is that we construct another degree 2.5 PRG. So there's going to be a leakage like before. And but this time around, we will be able to argue security using standard assumptions. That's the main idea. Still the same kind of PRG, but we are going to argue security. This time, we're going to work with Boolean inputs and outputs. So your input is going to be a Boolean vector in 0, 1 to the n. So there are n bits, right? Your output is going to be a PRG in NC0 applied on this input, sigma. So this is nice. This is what you want, a PRG computed on the seed sigma. But as I've told you before, we go to pay a cost, there's a price, and the price comes in the form of a leakage. This leakage is different. So now I want you to be slightly attentive. This leakage is different in the sense that this sigma, this n bits. So I'm going to have n set of noisy linear equations, but this time there will be LPN samples instead of LWE encrypting each sigma. So let's see. So it'll be AI, these are coefficient vectors, and then inner product of AI with the secret S. And then I'm going to add a sparse vector EI, sparse error noise, which is chosen from the LPN distribution EI. So EI is sampled from the LPN distribution, and then plus sigma I mod P. Okay, so what's the difference in the previous thing and this thing? The difference is that there's a sparse error that is added to this sigma. Mainly in the previous thing, what we were getting was that there were some polynomials with input E, and then there were LW samples using the same error E. Now the error is much different. It looks like this EI plus sigma I. And this error is from LPN distribution. Okay, so now again, you'll ask two questions. Why is this helpful? And why is it secure? Those are two natural questions. Let's look at why is it helpful? Well, If you ignore this and just ask, can you compute it using bilinear maps? You cannot. The minimum degree that you need is at least 3. So you cannot compute it using bilinear maps. But the point is, if I give you this LPN leakage, then what we show in this work is that you can devise a short seed, which depends on the secret and the sparse error vector, so that now this PRG computation becomes degree 2 over this new seed, where the coefficient of those polynomials depend on a simple fashion on this LPN samples encrypting sigma. That's kind of the main idea. We are able to devise this short seed, which lets you do that. And I'm going to tell you later on how this evaluation works, what is the short seed and how it's computed, what are the degree 2 polynomials. I'm going to tell you next. But first, I want to just recap once again what just happened. So the main idea is, if you compare it from the previous degree 2.5 PRGs, if I had a seed sigma here, I'll just have sigma here and there will be no E. Like if I did not have these EIs here, then of course I can compute it using bilinear maps using the similar kind of tricks. But now I have a sparse error EI that's added to this thing. The point is that even if this is sparse, I'm still able to devise a short seed, which lets me compute it as a degree 2 polynomial. But the main point is that just that I've added a sparse error here, this gives me enough independence between these two parts in the form of LPN samples so that I can argue security. That's the main point. Okay, and I'm going to tell you the proof in just a while. In fact, the proof is really trivial. I could have done it in this slide, but I'm going to do it on the next slide. And Amit also did it on just half a slide. So the proof is really trivial. So the main theorem is that we're going to prove security assuming LPN and PRGs in NC0. That's the security proof. So you have AI, AIS plus EI plus sigma and G of sigma. That's your instance. Now, I know that AIS plus EI by LPN assumption, I can replace it with uniform because this error does not come on the right-hand side. Okay, it's not in the G of sigma. So I get this. Now, note that uniform plus any fixed element is just uniform. So it's identical to just having uniform. So this is indistinguishable to AI comma uniform and G of sigma. Now note that the seed sigma is no longer on the left-hand side. Therefore, I can replace G of sigma with a random string of length m. That's by PRG security. And that's it. That completes the proof. And there is nothing that I've hidden from you. And that completes half of the goal, which is just to show that this is secure. Now I have to tell you how it's implemented. So just to, again, drive away the point home, the main reason why we were able to argue security is the fact that this sparse error that's added here lets me argue using LPN assumption, the error that doesn't show up on the PRG part. This is where our new assumption differs from the previous assumption. So does anyone have any questions about this, about the security and the overall structure of our PRG? Sounds good. Okay, so what's remaining? I want to tell you how you implement it using bilinear maps and what does it even mean to be implementable by bilinear maps. So those two things. So SPRG construction details. Now, what is a structured seed PRG? It's a PRG which is going to have some structured seed and some structured evaluation. That's the main goal. So let me now kind of recall the definition of structured seed PRG. Rachel also did it in part 2, but just for the sake of completeness, let me do it. So it's going to have following algorithms. There's going to be an index sampling algorithm. Index sampling meaning it outputs a description of your PRG function. So it takes two parameters, lambda, which controls the level of security we want, and then n. N controls the length of the input. And you should really think throughout. N is arbitrary polynomial in lambda. Okay, so it's an arbitrary polynomial lambda, and it outputs an index. And the seed sampling algorithm is going to take this index, and it's going to output a seed. Now here is where it's differing from the conventional PRG. In a conventional PRG, there's only just the secret part of the seed, which is typically a random string. Here, the seed is going to have two strings, P and S. P stands for the public part of the seed. S stands for the secret or the private part of the seed. Okay, and the intuition is that the P part will be revealed to the adversary. And they might be arbitrarily structured. They don't have to be random string, just like in a traditional PRG. The point is that seed is now structured in this way, and the size of the seed, you can think of it as n times polynomial in lambda. Remember, n was the length parameter, so it kind of dictates the length of the seed. And then there is an evaluation algorithm which takes in your seed and outputs a Boolean string in 0, 1 to the m. Okay, and just to connect the dots, looking ahead, the public part of the seed will have this leakage that I was mentioning about, this LPN leakage, AIS plus EI plus sigma I, where the evaluation will be G of sigma. So this will be revealed to the adversary, and this will also be, once you compute the PRG output is actually G of sigma. Now it has this traditional conventional properties like any PRG. It needs to be expanding. What do I mean? The number of output bits have to be much more than the size of the seed. Okay. Then there is a security, which is a straightforward generalization of security of a regular PRG. Given the index, given the public part of the seed like this, the output that you compute, this output looks computationally close to random string of length m. So that's the security. Now the missing piece. What does it mean to be implementable by linear maps? So so Rachel told us in detail what it means. Let me now recall it. This is what I exactly mean. So when you look at the order of the linear map, P, so when you look at ZP, then each output bit should be computable by some constant degree polynomial over P and S over the seed, such that it's restricted to the fact that it's just degree 2 over the secret part of the seed. So remember, bilinear map only let you compute degree 2 functions in the secret values. So that's why that restriction is coming from. And formally what we need is that each output bit can be written as some constant degree polynomial over ZP, which is just degree 2 over the secret part of the seed. Okay, so that's kind of the computational model that we are looking at. We want a PRG with short seed, and the evaluation lies in this complexity. Okay, is the model clear? Okay, so how, just straight right into the construction. How do we construct this? So let me start by the main goal. Okay, so this is the desiderata. This is what you want to do. You will set this index as these coefficient vectors for the LPN sample. The public part of the seed will consist of these LPN samples encrypting sigma. So just let me remind you, AI was and S was chosen from ZP to the L. This error was chosen according to the LPN error distribution. And then the seed sigma is an n-bit seed, which is chosen at random. And we're going to use this PRG in NC0 somehow, which is a constant degree D PRG. Remember, PRG in NC0 can be written as a constant degree polynomial over the reals. Let's say degree D is that degree. Okay, it's a constant degree multilinear polynomial. And it's going to have a stretch of n to the 1 plus tau, which I'm going to denote as m. Okay, so that's the sampling details, but to just keep in the back of your mind. So the public seed is going to have this. Now the goal is just to come up with a private part of the seed, a short seed, which has two requirements. First, I should be able to compute G of sigma, PRG evaluated at sigma, in this complexity model. Each output bit is some constant degree polynomial, which is degree 2 over the seed, mod P. And I want that the size of this private part of the seed should be short, should be small, it should be much less than the number of output bits. These are the two requirements that I want. And now rest of this talk will just be about how do I come up with such a seed. Okay, so the fact that we use these LPN samples to encode this seed was already very helpful. And in fact, I claim that the half the battle is already won. Okay, it's already won. Why? Because what I can do, I can define a new private part of the seed. What does it have? It's going to have, so remember our PRG was degree D over the reals, right? So what I'm going to do, take the secret and pre-compute all the monomials up till degree D over 2 and put it in the private part of the seed. Okay. And now you might ask, oh, this is too big, but actually I'm going to set the dimension appropriately, dimension of the secret, so that it's not too big. I'm going to set the dimension so that the number of monomials is equal to n. So that's fine. Okay, I can put it. But now, why is it helpful? Let's see. So let's look at this computation that I'm going to do. Y prime, the output that you are going to compute. This is this polynomial g of the PRG. G can be written as a polynomial over with integer coefficients, right? So I'm going to just write that, but compute this polynomial over mod p, where the inputs will be b minus as. So remember, I have pre-computed monomials of s inside. So this is the polynomial that I'm going to compute. Now, why can I compute this? I can compute this because g is a degree d polynomial. Therefore, it's degree d over b. But b is public, so that's fine. It's a constant degree polynomial over the public part. Then it's degree d over a, but a is also public, so therefore that's also fine. The missing piece is degree d over the secret s. But the point is, I have already pre-computed the monomials of degree d over 2 in the private part of the seed. Therefore, it's just degree 2 over the private part of the seed. Okay, so I computed this polynomial. Now, what's the point? So I can compute it in the required complexity class. The point is this b minus as is just sigma plus e. You can see it from this equation. So I can compute this g of sigma plus error mod p. So it's a okay. But now observe that each of the error is it's 0 with a very large probability, 1 minus 1 by L to the delta. It's only with 1 by L to the delta probability that it's non-zero. So it's 0 with very large probability, but it's with tiny probability it's non-zero. Therefore, and the fact, and observe the fact that this is a PRG in NC0. So every output bit of this PRG only depends on a constant number of inputs, and most likely fix any output bit. For that output bit, most likely all of the input bits that it depends on will have unadulterated values. So the errors for those will be 0 with very large probability. In fact, you can compute it, probability that the ith output bit y prime equal to the desired output ith bit, that is g of sigma ith bit, that's at least 1 minus 1 by L to the delta to the power locality, because this is the probability that all the inputs that it depends on are 0. Sorry, all the errors in the inputs that it depends on, that's 0. So this is what you get, and this is a very large probability, 1 minus order L to the minus delta. Now it just means that most likely any given bit is going to be correct, and it's only L to the minus delta fraction of the m outputs that are incorrect. Okay, so you can compute it, we can formalize it. Let me call bad, as the name suggests, these are bad output indices. Output indices where I don't get the correct value. In expectation, the size is going to be less than m by L to the delta. This is just by linearity of expectation, because L to the delta was L to the minus delta was the probability that it is bad. So I can compute this. And by Markov argument, the size that this bad exceeds lambda folds more than the expectation is less than 1 by lambda. This is just standard Markov. For any given parameter lambda, if you are exceeding more than m by L to the delta by lambda folds, that's less than 1 by lambda. So our goal for this rest of this talk is that I'm going to just focus on correcting m lambda by L to the delta errors in the output. And that's my goal. I just want to correct in a way securely and while preserving expansion, only m lambda by L to the delta errors. Now, it might happen that you have more errors with 1 by lambda probability, but in that case, I'm just going to give up. I'm going to lose 1 by lambda in the security. And Rachel told us how to manage those issues by security amplification. So I'm going to just focus on this. Okay, so now let's take a first attempt at this. How do we do it? What's the first naive idea, which of course doesn't work? I'm going to define this correction vector, which is g of sigma. That's the desired computation, minus g of sigma plus e. That's what you can compute using this complexity model. So you compute this. Now, somehow, let's say I put the correction in the private part of the seed. Let's say I put it in the private part of the seed. And if I'm able to compute this, y prime is equal to g of sigma plus correction. then I know that has to be correct because that's how I define this correction vector, right? It's g of sigma minus g of sigma plus e. And if I add correction, then I'm going to get this. And this is in the required complexity class. But the main problem with this naive idea is that the correction vector is of the length of the PRG. If the length of the output bit of output length of the PRG is m, size of this correction is also m. So it is also the size of this is m, and therefore there's no stretch. You don't get anything. You cannot. You have to do something non-trivial. So the point is we are going to use the fact that correction is sparse. As I told you before, the number of errors is m lambda by L to the delta. So it's only 1 by L to the delta fraction. I need to use the fact that this correction is sparse. One naive attempt is that I can just put the non-zero entries, those corresponding to the bad set, and somehow reveal either the bad here or in the public part of the seed and somehow compute this. So y prime is g of I plus sigma when I is not bad, meaning if it's correct, don't correct it. And if it's incorrect, then you correct it. So this is a naive attempt that you will do. First of all, it's not clear how to achieve it in this complexity model, but even if I did that, this is a fundamental problem by just naively putting the correction non-zero entries in the private part of the seed. The main issue is that if I leak out this set bad in the public part or the index, leaking out is fatal because it is going to leak out which of the LPN samples have zero errors. And that's detrimental to LPN security. So I want you to trust on me that I cannot leak out this set of bad wherever you have non-zero, where you have incorrect entries. If I leak that, I'm going to hurt LPN security. So I cannot do that. Does anyone have any questions at this point? Just please interrupt me. Otherwise, I'll just keep going. Sounds good. So that's where we were. We want to now, hopefully the rest of the goal is clear. The goal is that I want to put this correction vector in a way that does not leak out which of the indices are bad. That's my goal. So let's try to look at with a simple test case, and that's a solution that will work for the simple test case. So the test case is assume that the correction is one sparse, meaning there's only one entry in the PRG whole output length that needs correction. Okay, and our goal is to just correct that. Now I claim that I can leverage the fact that it is sparse along with matrix factorization to achieve our goal. So why? So I'm going to define a grid. Okay, and let's say the size of the grid is root m cross root m. So the total number of entries in this grid is m. That's the number of PRG output bits. Okay, so I define a grid like that. Now I'm going to sample a map. What it does, it maps the PRG output bits in one-to-one onto manner onto this grid. So it's just arbitrary map, doesn't have to be random or anything. It's just any map you want. It maps the PRG output bits into this correction vector, into this matrix. And then I'm going to fill this matrix using the correction entries. So take this correction, use this bijection and fill it. Using this m of phi I, the matrix at index phi I is correction at entry I. And then I want you to observe that it's one sparse because the size, the density of the correction vector was 1. I assumed that the number of bad output is 1. So it's one sparse, therefore it's rank 1. Therefore I can factor this matrix M as U times V, where both U and V transpose are in ZP root M plus 1. Remember, root M was the length, 1 was the rank, so therefore it's U times V. Both of the dimensions for U and V are root M cross 1. Now that's it. That's the bulk of the work. I can put U and V inside the private part of the seed. I can put this function phi map in the index, and then I can compute y prime as g of I sigma plus e. That's what you could already do it. Plus this matrix U times V. That will reconstruct the matrix M. But I'm going to query it at the index phi of I. That's where I know the correction index for index I sits. Okay. Now the point is, this is a degree 2 function in U and V. Okay, so you can compute this. And phi is public. So this is completely like a fixed degree 2 polynomial over the private part of the seed. So this is in the required complexity class. So you can compute this. But the point is that when you look at the stretch is the size of, if you look at, you also only want to show that the size of the seed is small. So look at the size of the public part of the seed. That's n log p. They are n LPN samples. Size of the secret part of the seed consists of these monomials. These monomials, I have already fixed the dimension so that the size of the number of monomials is n log p. Then I have to count the size of u and v. I showed in the previous slide that a dimension of u and v are root m cross 1. Therefore, the size of u and v is like proportional to root m. But this is much less than m. So therefore, we are good stretch-wise. And security-wise, we are also good. Note that this phi is the only thing that is leaked out, and phi is completely independent of the bad output bits. So it doesn't leak anything in terms of security. The same argument that you saw works for arguing security. So the key takeaway from this is that this corrects one error. In fact, actually, you can make this idea work as long as the number of errors are bounded by m to the 0.49. I mean, this will become m to the 0.99 here, and still that's much less than m, and the security will work until these many errors. But the main point is we need to correct much more than that. We need to correct m lambda by L to the delta errors, and that is where we want to do some work. Because m lambda by L to the delta is actually linear in m. It's not m, like m to the 0.49 is much less than this. So the goal is to correct these many errors. So this idea won't work, but what we show in this paper is that an extension of this idea works. So I'm going to define, so where I had one giant bucket of size root m cross root m, if I want to correct these many errors, m lambda by L to the delta, why don't I just set t buckets instead of one, t smaller buckets? So I'm going to define m1 through mt. Each of these buckets is of small size. So let's say L to the delta over 2 times L to the delta over 2. Therefore, each buckets have only L to the delta elements. The total number of entries combined in all the buckets is m lambda, which is much more than m. So I'm going to set these buckets. Now I do the same exercise. I'm going to sample random maps. This time the maps need to be random for just our calculations and stuff to work out. But they are random maps. What do? They take the output bits of the PRG, so m output bits, and just spread it out in these buckets injectively. Okay, so without loss of generality, you can think of two functions, phi bucket and phi index. This is only for the sake of convenience. Phi bucket will tell me which bucket every output bit goes to, and phi index tell me which index in the corresponding bucket that each output is going. So phi bucket will tell me, okay, first output will go to the 7th bucket. Phi index will tell me the first output bit is going to index 2, 3 in that bucket. That's exactly what it's doing. So they are just two random functions. And now the same exercise. I'm going to take the correction, map it into these. Now what's the point? I have mapped it using random functions. I want you to observe the number of buckets is T, capital T. The number of errors that you wanted to correct is also T. Therefore, in expectation, every bucket is getting one error. And we can also actually prove a stronger claim just because of the fact we are using random maps. We can prove that with very large probability, 1 minus e to the power minus lambda, each of them will get at most a lambda number of non-zero entries. This is just standard Chernoff kind of argument. You can prove that each of them is going to just get at most lambda elements. Therefore, rank of each of them with very large probability is going to be less than lambda. So same thing, I'm going to factor each of them. Ui times Vi, where the dimension grows now like Zp root L to the delta times lambda. Remember, L to the delta over 2 was the length, lambda is the rank, therefore this is the dimension. I factor it. And I do the same thing again. I put it in the private part of the seed, these Uis and Vi's. And then in the index, I'm going to put this new function phi, which is a random function. So now the computation is an obvious extension of the previous computation. Y prime is gi of sigma plus e plus u phi bucket I times v phi bucket I evaluated at phi index. So what is it doing? It's looking at entry I, and I know that the correction I sits in phi bucket I matrix. So that's it's recomputing this matrix, the bucket corresponding to the ith correction, and it's probing it at the correct location, phi index of I. That's all it is doing. And this is some nice degree 2 polynomial in U and V. And phi is public, so it's in the required complexity class. So then I compute this and note that this is equal to exactly correction I, and this will get us the desired output. So security wise, we are good because this phi is independent of the bad set, and you're not leaking anything beyond the LPN samples and the PRG output. So security wise, we are good. But now when it comes to stretch, this is where we have to be slightly careful. Now, because it's a slightly non-trivial argument as compared to the previous argument, if you look at the size of the public part of the seed, that's already n log p, which is good. The size of the private part of the seed is just the size of the number of monomials. That we ensured was n log p. The remaining part was the size of ui's and vi's. There are capital T matrices, and each of them have size about the same. And I calculated from the previous slide, the size of each matrix is lambda times root L to the delta, and T was m lambda by L to the delta. So when I plug in all the values, I get this number, m lambda square by L to the delta over 2. Question is this less than m? Well, if I'm intelligent enough, I can set the parameters for L so that this is actually much less than m. You're going to set L a large enough polynomial in lambda such that actually it's much less than m. And that's the saving that we are getting, which turns out it's sufficient for IO. That's the minuscule saving. Just note that it's linear in m, just like a saving of 1 by L to the delta over 2 factor. Turns out that's the only thing that saves us and gets us to IO. So that's it. That concludes our construction. In the security proof I've already covered, and that's about the construction. And does anyone have any questions at this point? Okay, sounds good. So let me summarize. What did we get from this? So we are going to learn these LPN samples, encrypting sigma and the PRG output at sigma with probability 1 minus 1 by lambda. That's the same probability where the number of bad output bits are not too many. With 1 by lambda probability, we are learning something else. So we're going to lose 1 by lambda in security, and 1 minus 1 by lambda security, we can immediately argue from LPN and PRG security. This is the same argument that I showed a few minutes ago. So you can argue a weak security for this PRG. So this lets us construct weakly secure SPRG. And then I'll plug it in back into this picture. I get weak SPRG from PRG and NC0 and LPN, and that's it. That kind of completes the picture, and that'll give you IO. So yeah, that's it. And then once you have this, and you have all these tools ready, then you can apply the same compiler, and this will give us IO. And I'll refer you to the tutorial by Rachel for more details about how these steps work. So with that, let me conclude on the note of some open problems. One of the main open problems, according to the 3 authors, is that can you construct provably secure post-quantum secure IO from well-founded assumptions? In particular, for our line of work, it will mean that you need to remove the reliance on the bilinear map assumptions, because those are the only ones which are known to be post-quantum broken. And as far as we can see, all of the other assumptions look plausible post-quantumly. This is a really exciting time for IO research. There have been several exciting works which came together with our work. In particular, they construct IO assuming strong circular security conjectures on fully homomorphic encryptions. And that's the only assumption, and as far as we can tell, that can be plausibly post-quantum. Still, that those assumptions are new, but what's nice about those assumptions are that they are considerably much more simpler from previous works. And we hope one day either that line of work or some other line of work converges to this question of secure post-quantum IO. One of the most pressing open question is, can you make progress on the efficiency front? So far, all of the candidates are horrendously inefficient, and is it possible to construct something hopefully implementable from well-founded or even in fact simple to state assumptions? So that's one of the biggest problems. And finally, probably one of the simpler problems is, can you give us another approach which yields IO from some other well-founded assumptions? Like there are so many out there. Doesn't have to be post-quantum, but some other set of assumptions. So these are the 3 open questions. And if you have any questions, just please feel free to ask. And you can also shoot an email to any 3 of us, and we're happy to answer.
Please join me in thanking the speakers of the session for their remarkable presentation and congratulating them on this breakthrough result. We have a few minutes for questions. If there are questions, feel free to just use the audio channel.
Hi, Aayush. I had one question. Firstly, thanks for the great talk to all 3 of you. Like really exciting. I had one question from your last slide on the efficiency part. So I was just wondering, where would you even start simplifying for the efficiency part? I mean, it's a long line of things you do, right? Like the amplification and then the structure seed PRG and all the assumptions. But I mean, what do you see as the first step in going towards the efficiency part?
So unfortunately, I have no idea about this, if this line of work can ever lead to a efficient construction, because there are so many bootstrapping steps involved. So if you were to work with this line, you'll probably need to remove some of the bootstrapping steps, and that's the first goal. But the other works that have recently come up dealing with the efficiency issues, they typically work directly with circuits, and they encode circuits in using some new mathematical objects and assumptions, and that's what they try to do. And those yield much more efficient obfuscation schemes. But again, we are not sure about the assumptions because they are completely the nature is completely new, and it'll only take time will tell how those assumptions fare. So I feel that if you were to work with this line, you need to remove some of the bootstrapping steps and give us just clean the clutter a bit to get more direct constructions. The main step is this FE to IO transformation. This is really complicated. Like functional encryption to IO, that's really complicated.
Yeah, I think just streamlining is another major direction now for us to explore, sort of how to streamline this this route and other routes as well to getting to IO.
Got it. Thank you.
See if there are any other questions.
So just one more question. So I was also wondering, for the post-quantum secure IO, what's the, so you told that SXTH assumption is the one you need to remove, but do you also see any direction to doing that, or any thoughts or anything?
So who wants to take this? Should I?
I mean, we all just have
Sure.
to get
Yeah, go ahead.
Okay. So unfortunately, it's just the entire approach that we are working with right now, it's very tailor-made to work with bilinear maps. We're assuming that we have a kind of a pseudo obfuscation for degree 2 polynomials, and we are kind of bootstrapping and leveraging its power to build something bigger. And so the whole approach seems pretty tailor-made for that. And in my opinion, it will require fundamentally different and new ideas to get rid of the bilinear map from our setting, at least.
So I think a first sort of intermediate goal would be to get FE for, let's say, quadratic functions from some other assumption, from some other post-quantum assumption. So I think that's something that we would probably want to attack first. And once we can get that, then we can hope to do the other things that allow for partially hiding functional encryption, and then potentially take that route. So that's sort of one route. But as Aayush mentioned, we first have this pretty interesting thing to overcome if we're taking our route. Of course, there could be completely different routes as well.
Thank you.
Yeah, I think partially why the new works are so very attractive that they only work with lattices, that they don't use other assumptions. But on the other hand, that it is then difficult to, like, the reason we use bilinear map is because bilinear map is a mini version of obfuscation, as Aayush said, that it's for very small degree, but albeit it is, but nevertheless, it's a small version of obfuscation. But lattices doesn't have this feature, and that's why their assumptions are kind of new assumptions. So there's always a trade-off, but you never know. Maybe at some point that will have constructions just based on RWE.
That's the dream.
But right now the state of affairs in like lattice world is pretty unclear. There was a work which suggested that degree 2 FE from lattices with some requirements should be impossible to achieve, and now there are these works which make a different assumption, but they're able to get to all the way to IO, and like it's still like yet to be figured out what exactly needs to be the right model to target.
Thank you.